Part 2 Chapter 1 Outer Space. Outer space, commonly shortened to space, is the expanse that exists beyond Earth and its atmosphere and between celestial bodies. Outer space is not completely empty, it is a hard vacuum containing a low density of particles, predominantly a plasma of hydrogen and helium, as well as electromagnetic radiation, magnetic fields, neutrinos, dust, and cosmic rays. The baseline temperature of outer space, as set by the background radiation from the Big Bang, is 2.7 kelvins, (270.45 degrees Celsius, 454.81 degrees Fahrenheit). The plasma between galaxies is thought to account for about half of the baryonic, ordinary, matter in the universe, having a number density of less than 1 hydrogen atom per cubic meter and a temperature of millions of kelvins. Local concentrations of matter have condensed into stars and galaxies. Studies indicate that 90% of the mass in most galaxies is in an unknown form, called dark matter, which interacts with other matter through gravitational but not electromagnetic forces. Observations suggest that the majority of the mass energy in the observable universe is dark energy, a type of the vacuum energy that is poorly understood. Intergalactic space takes up most of the volume of the universe, but even galaxies and star systems consist almost entirely of empty space. Outer space does not begin at a definite altitude above the Earth's surface. The Kármán line, an altitude of 100 kilometers, 62 miles, above sea level, is conventionally used as the start of outer space and space treaties and for aerospace records keeping. The framework for international space law was established by the Outer Space Treaty, which entered into force on October 10, 1967. This treaty precludes any claims of national sovereignty and permits all states to freely explore outer space. Despite the drafting of UN resolutions for the peaceful uses of outer space, anti-satellite weapons have been tested in Earth orbit. Humans began the physical exploration of space during the 20th century with the advent of high-altitude balloon flights. This was followed by crewed rocket flights and, then, crewed Earth orbit, first achieved by Yuri Gagarin of the Soviet Union in 1961. Due to the high cost of getting into space, human spaceflight has been limited to low Earth orbit and the Moon. On the other hand, uncrewed spacecraft have reached all of the known planets in the solar system. Outer space represents a challenging environment for human exploration because of the hazards of vacuum and radiation. Microgravity also has a negative effect on human physiology that causes both muscle atrophy and bone loss. In addition to these health and environmental issues, the economic cost of putting objects, including humans, into space is very high. Formation and state. The size of the whole universe is unknown, and it might be infinite in extent. According to the Big Bang theory, the very early universe was an extremely hot and dense state about 13.8 billion years ago, which rapidly expanded. About 380,000 years later, the universe had cooled sufficiently to allow protons and electrons to combine and form hydrogen, the so-called recombination epoch. When this happened, matter and energy became decoupled, allowing photons to travel freely through the continually expanding space. Matter that remained following the initial expansion has since undergone gravitational collapse to create stars, galaxies and other astronomical objects, leaving behind a deep vacuum that forms what is now called outer space. As light has a finite velocity, this theory also constrains the size of the directly observable universe. The present-day shape of the universe has been determined from measurements of the cosmic microwave background using satellites like the Wilkinson Microwave Anisotropy Probe. These observations indicate that the spatial geometry of the observable universe is flat, meaning that photons on parallel paths at one point remain parallel as they travel through space to the limit of the observable universe, except for local gravity. The flat universe, combined with the measured mass density of the universe and the accelerating expansion of the universe, indicates that space has a non-zero vacuum energy, which is called dark energy. Estimates put the average energy density of the present-day universe at the equivalent of 5.9 protons per cubic meter, including dark energy, dark matter, and baryonic matter, ordinary matter composed of atoms. The atoms account for only 4.6% of the total energy density, or a density of 1 proton per 4 cubic meters. The density of the universe is clearly not uniform. It ranges from relatively high density in galaxies, including very high density in structures within galaxies, such as planets, stars, and black holes, to conditions in vast voids that have much lower density, at least in terms of visible matter. Unlike matter and dark energy seems not to be concentrated in galaxies. Although dark energy may account for a majority of the mass energy in the universe, dark energy's influence is 5 orders of magnitude smaller than the influence of gravity from matter and dark matter within the Milky Way. Environment. Outer space is the closest known approximation to a perfect vacuum. It has effectively no friction, allowing stars, planets, and moons to move freely along their ideal orbits, following the initial formation stage. The deep vacuum of intergalactic space is not devoid of matter, as it contains a few hydrogen atoms per cubic meter. By comparison, the air humans breathe contains about 1,025 molecules per cubic meter. The low density of matter in outer space means that electromagnetic radiation can travel great distances without being scattered. The mean free path of a photon in intergalactic space is about 1,023 kilometers, or 10 billion light-years. In spite of this, extinction, which is the absorption and scattering of photons by dust and gas, is an important factor in galactic and intergalactic astronomy. Stars, planets, and moons retain their atmospheres by gravitational attraction. Atmospheres have no clearly delineated upper boundary. The density of atmospheric gas gradually decreases with distance from the object until it becomes indistinguishable from outer space. The Earth's atmospheric pressure drops to about 0.032 pascals at 100 kilometers, 62 miles, of altitude, compared to 100,000 pascals for the International Union of Pure and Applied Chemistry (UPAC) definition of standard pressure. Above this altitude, isotropic gas pressure rapidly becomes insignificant when compared to radiation pressure from the sun and the dynamic pressure of the solar wind. The thermosphere in this range has large gradients of pressure, temperature and composition, and varies greatly due to space weather. The temperature of outer space is measured in terms of the kinetic activity of the gas, as it is on Earth. The radiation of outer space has a different temperature than the kinetic temperature of the gas, meaning that the gas and radiation are not in thermodynamic equilibrium. All of the observable universe is filled with photons that were created during the Big Bang, which is known as the cosmic microwave background radiation, CMB. There is quite likely a correspondingly large number of neutrinos called the cosmic neutrino background. The current blackbody temperature of the background radiation is about 3 K, 270 degrees Celsius, 454 degrees Fahrenheit. The gas temperatures in outer space can vary widely. For example, the temperature in the Boomerang Nebula is 1 K, while the solar corona reaches temperatures over 1.2 to 2.6 million K. Magnetic fields have been detected in the space around just about every class of celestial object. Star formation in spiral galaxy can generate small-scale dynamos, creating turbulent magnetic field strengths of around 5 to 10 G. The Davis-Greenstein effect causes elongated dust grains to align themselves with a galaxy's magnetic field, resulting in weak optical polarization. This has been used to show ordered magnetic fields exist in several nearby galaxies. Magnetohydrodynamic processes in active elliptical galaxies produce their characteristic jets and radio lobes. Non-thermal radio sources have been detected even among the most distant, high-Z sources, indicating the presence of magnetic fields. Outside a protective atmosphere and magnetic field, there are few obstacles to the passage through space of energetic subatomic particles known as cosmic rays. These particles have energies ranging from about 106 electron volts up to an extreme 1020 electron volts of ultra-high energy cosmic rays. The peak flux of cosmic rays occurs at energies of about 109 electron volts, with approximately 87% protons, 12% helium nuclei and 1% heavier nuclei. In the high-energy range, the flux of electrons is only about 1% of that of protons. Cosmic rays can damage electronic components and pose a health threat to space travelers. According to astronauts, like Don Pettit, space has a burned, metallic odor that clings to their suits and equipment, similar to the scent of an arc-welding torch. Regions. Space is a partial vacuum. Its different regions are defined by the various atmospheres and winds that dominate within them, and extend to the point at which those winds give way to those beyond. Geospace extends from Earth's atmosphere to the outer reaches of Earth's magnetic field, whereupon it gives way to the solar wind of interplanetary space. Interplanetary space extends to the heliopause, whereupon the solar wind gives way to the winds of the interstellar medium. Interstellar space then continues to the edges of the galaxy, where it fades into the intergalactic void. Geospace. The lower half is a blue-white planet in low illumination. Nebulous red streamers climb upward from the limb of the disk toward the black sky. The space shuttle is visible along the left edge. Geospace is the region of outer space near Earth, including the upper atmosphere and magnetosphere. The Van Allen radiation belts lie within the geospace. The outer boundary of geospace is the magnetopause, which forms an interface between the Earth's magnetosphere and the solar wind. The inner boundary is the ionosphere. The variable space weather conditions of geospace are affected by the behavior of the Sun and the solar wind. The subject of geospace is interlinked with heliophysics, the study of the Sun and its impact on the planets of the solar system. The dayside magnetopause is compressed by solar wind pressure. The subsolar distance from the center of the Earth is typically 10 Earth radii. On the night side, the solar wind stretches the magnetosphere to form a magnetotail that sometimes extends out to more than 100 to 200 Earth radii. For roughly 4 days of each month, the lunar surface is shielded from the solar wind as the moon passes through the magnetotail. Geospace is populated by electrically charged particles at very low densities, the motions of which are controlled by the Earth's magnetic field. These plasmas form a medium from which storm-like disturbances powered by the solar wind can drive electrical currents into the Earth's upper atmosphere. Geomagnetic storms can disturb two regions of geospace, the radiation belts and the ionosphere. These storms increase fluxes of energetic electrons that can permanently damage satellite electronics, interfering with shortwave radio communication and GPS location and timing. Magnetic storms can also be a hazard to astronauts, even in low Earth orbit. They also create aurora seen at high latitudes in an oval surrounding the geomagnetic poles. Although it meets the definition of outer space, the atmospheric density within the first few hundred kilometers above the Kármán line is still sufficient to produce significant drag on satellites. This region contains material left over from previous crewed and uncrewed launches that are a potential hazard to spacecraft. Some of this debris re-enters Earth's atmosphere periodically. Cislunar space. Earth's gravity keeps the Moon in orbit at an average distance of 384,403 kilometers, 238,857 miles. The region outside Earth's atmosphere and extending out to just beyond the Moon's orbit, including the Lagrange points, is sometimes referred to as cislunar space. Deep space is defined by the United States government and others as any region beyond cislunar space. The International Telecommunication Union, responsible for radio communication, including satellites, defines the beginning of deep space at about 5 times that distance, to 106 kilometers. The region where Earth's gravity remains dominant against gravitational perturbations from the Sun is called the Hill sphere. This extends into translunar space to a distance of roughly 1% of the mean distance from Earth to the Sun, or 1.5 million kilometer, 0.93 million mile. Interplanetary space. Main article, Interplanetary medium. At lower left, a white coma stands out against a black background. Nebulous material streams away to the top and left, slowly fading with distance. The sparse plasma, blue, and dust, white, in the tail of comet Hale-Bopp being shaped by pressure from solar radiation and the solar wind, respectively. Interplanetary space is defined by the solar wind, a continuous stream of charged particles emanating from the Sun that creates a very tenuous atmosphere, the heliosphere, for billions of kilometers into space. This wind has a particle density of 5 to 10 protons/cm3 and is moving at a velocity of 350 to 400 kilometers per second, 780,000 to 890,000 miles per hour. Interplanetary space extends out to the heliopause where the influence of the galactic environment starts to dominate over the magnetic field and particle flux from the Sun. The distance and strength of the heliopause varies depending on the activity level of the solar wind. The heliopause in turn deflects away low-energy galactic cosmic rays, with this modulation effect peaking during solar maximum. The volume of interplanetary space is a nearly total vacuum, with the mean free path of about 1/8 astronomical unit at the orbital distance of the Earth. This space is not completely empty, and is sparsely filled with cosmic rays, which include ionized atomic nuclei and various subatomic particles. There is also gas, plasma and dust, small meteors, and several dozen types of organic molecules discovered to date by microwave spectroscopy. A cloud of interplanetary dust is visible at night as a faint band called the zodiacal light. Interplanetary space contains the magnetic field generated by the Sun. There are also magnetospheres generated by planets such as Jupiter, Saturn, Mercury and the Earth that have their own magnetic fields. These are shaped by the influence of the solar wind into the approximation of a teardrop shape, with the long tail extending outward behind the planet. These magnetic fields can trap particles from the solar wind and other sources, creating belts of charged particles such as the Van Allen radiation belts. Planets without magnetic fields, such as Mars, have their atmospheres gradually eroded by the solar wind. Interstellar space. Main article, Interstellar medium. Interstellar space redirects here. For the album, see Interstellar space. Patchy orange and blue nebulosity against a black background, with a curved orange arc wrapping around a star at the center. Bow shock formed by the magnetosphere of the young star LL Orionis, center, as it collides with the Orion nebula flow. Interstellar space is the physical space within a galaxy beyond the influence each star has upon the encompassed plasma. The contents of interstellar space are called the interstellar medium. Approximately 70% of the mass of the interstellar medium consists of lone hydrogen atoms, most of the remainder consists of helium atoms. This is enriched with trace amounts of heavier atoms formed through stellar nucleosynthesis. These atoms are ejected into the interstellar medium by stellar winds or when evolved stars begin to shed their outer envelopes, such as during the formation of a planetary nebula. The cataclysmic explosion of the supernova generates an expanding shock wave consisting of ejected materials that further enrich the medium. The density of matter in the interstellar medium can vary considerably. The average is around 106 particles per cubic meter, but cold molecular clouds can hold 108 to 1012 per cubic meter. A number of molecules exist in interstellar space, as can tiny 0.1 m dust particles. The tally of molecules discovered through radio astronomy is steadily increasing at the rate of about 4 new species per year. Large regions of higher density matter known as molecular clouds allow chemical reactions to occur, including the formation of organic polyatomic species. Much of this chemistry is driven by collisions. Energetic cosmic rays penetrate the cold, dense clouds and ionize hydrogen and helium, resulting, for example, in the trihydrogen cation. An ionized helium atom can then split relatively abundant carbon monoxide to produce ionized carbon, which in turn can lead to organic chemical reactions. The local interstellar medium is a region of space within 100 parsecs (pc) of the Sun, which is of interest both for its proximity and for its interaction with the solar system. This volume nearly coincides with a region of space known as the local bubble, which is characterized by a lack of dense, cold clouds. It forms a cavity in the Orion arm of the Milky Way galaxy, with dense molecular clouds lying along the borders, such as those in the constellations of Ophiuchus and Taurus. The actual distance to the border of this cavity varies from 60 to 250 pc or more. This volume contains about 104 to 105 stars, and the local interstellar gas counterbalances the astrospheres that surround these stars, with the volume of each sphere varying depending on the local density of the interstellar medium. The local bubble contains dozens of warm interstellar clouds with temperatures of up to 7,000 K and radii of 0.5 to 5 pc. When stars are moving at sufficiently high peculiar velocities, their astrospheres can generate bow shocks as they collide with the interstellar medium. For decades it was assumed that the Sun had a bow shock. In 2012, data from Interstellar Boundary Explorer (IBEX) and NASA's Voyager probes showed that the Sun's bow shock does not exist. Instead, these authors argue that a subsonic bow wave defines the transition from the solar wind flow to the interstellar medium. A bow shock is the third boundary of an astrosphere after the termination shock and the astropause, called the heliopause in the solar system. Intergalactic space. Structure of the universe. Matter distribution in a cubic section of the universe. The blue fiber structures represent the matter, and the empty regions in between represent the cosmic voids of the intergalactic medium. A star-forming region in the Large Magellanic Cloud, perhaps the closest galaxy to Earth's Milky Way. Main articles: warm hat intergalactic medium, intercluster medium, and intergalactic dust. Intergalactic space is the physical space between galaxies. Studies of the large-scale distribution of galaxies show that the universe has a foam-like structure, with groups and clusters of galaxies lying along filaments that occupy about a tenth of the total space. The remainder forms huge voids that are mostly empty of galaxies. Typically, a void spans a distance of 10 to 40 h?1 mpc, where h is the Hubble constant in units of 100 kilometers s?1 mpc?1, or the dimensionless Hubble constant. Surrounding and stretching between galaxies, there is a rarefied plasma that is organized in the galactic filamentary structure. This material is called the intergalactic medium, IgM. The density of the IgM is 5 to 200 times the average density of the universe. It consists mostly of ionized hydrogen, i.e. a plasma consisting of equal numbers of electrons and protons. As gas falls into the intergalactic medium from the voids, it heats up to temperatures of 105 K to 107 K, which is high enough so that collisions between atoms have enough energy to cause the bound electrons to escape from the hydrogen nuclei. This is why the IgM is ionized. At these temperatures, it is called the warm hot intergalactic medium, WHIM. Although the plasma is very hot by terrestrial standards, 105 K is often called warm in astrophysics. Computer simulations and observations indicate that up to half of the atomic matter in the universe might exist in this warm hot, rarefied state. When gas falls from the filamentary structures of the WHIM into the galaxy clusters at the intersections of the cosmic filaments, it can heat up even more, reaching temperatures of 108 K and above in the so-called intercluster medium, ICM. Earth orbit. Main article: geocentric orbit. A spacecraft enters orbit when its centripetal acceleration due to gravity is less than or equal to the centrifugal acceleration due to the horizontal component of its velocity. For a low Earth orbit, this velocity is about 7,800 meters per second, 28,100 kilometers per hour, 17,400 miles per hour. By contrast, the fastest piloted airplane speed ever achieved, excluding speeds achieved by deorbiting spacecraft, was 2,200 meters per second, 7,900 kilometers per hour, 4,900 miles per hour, in 1967 by the North American X-15. To achieve an orbit, a spacecraft must travel faster than a suborbital spaceflight. The energy required to reach Earth orbital velocity at an altitude of 600 kilometers, 370 miles, is about 36 megajoules/kg, which is 6 times the energy needed merely to climb to the corresponding altitude. Spacecraft with a perigee below about 2,000 kilometers, 1,200 miles, are subject to drag from the Earth's atmosphere, which decreases the orbital altitude. The rate of orbital decay depends on the satellite's cross-sectional area and mass, as well as variations in the air density of the upper atmosphere. Below about 300 kilometers, 190 miles, decay becomes more rapid with lifetimes measured in days. Once a satellite descends to 180 kilometers, 110 miles, it has only hours before it vaporizes in the atmosphere. The escape velocity required to pull free of Earth's gravitational field altogether and move into interplanetary space is about 11,200 meters per second, 40,300 kilometers per hour, 25,100 miles per hour. Boundary. For the boundary of the universe, see observable universe. A white rocket ship with oddly shaped wings at rest on a runway. There is no clear boundary between Earth's atmosphere and space, as the density of the atmosphere gradually decreases as the altitude increases. There are several standard boundary designations, namely, the Fédération Aéronautique Internationale has established the Kármán line at an altitude of 100 kilometers, 62 miles, as a working definition for the boundary between aeronautics and astronautics. This is used because at an altitude of about 100 kilometers, 62 miles, as Theodore van Kármán calculated, a vehicle would have to travel faster than orbital velocity to derive sufficient aerodynamic lift from the atmosphere to support itself. The United States designates people who travel above an altitude of 50 miles, 80 kilometers, as astronauts. NASA's Space Shuttle used 400,000 feet, 122 kilometers, 76 miles, as its re-entry altitude, termed the entry interface, which roughly marks the boundary where atmospheric drag becomes noticeable, thus beginning the process of switching from steering with thrusters to maneuvering with aerodynamic control surfaces. In 2009, scientists reported detailed measurements with the Suprathermal Ion Imager, an instrument that measures the direction and speed of ions, which allowed them to establish a boundary at 118 kilometers, 73.3 miles, above Earth. The boundary represents the midpoint of a gradual transition over tens of kilometers from the relatively gentle winds of the Earth's atmosphere to the more violent flows of charged particles in space, which can reach speeds well over 268 meters per second, 600 miles per hour. Legal status. Main article, Space Law. See also, Bogotá Declaration. At top, a dark rocket is emitting a bright plume of flame against a blue sky. Underneath, a column of smoke is partly concealing a Navy ship. 2008 launch of the SM-3 missile used to destroy American reconnaissance satellite USA-193. The Outer Space Treaty provides the basic framework for international space law. It covers the legal use of outer space by nation-states, and includes in its definition of outer space, the Moon, and other celestial bodies. The treaty states that outer space is free for all nation-states to explore and is not subject to claims of national sovereignty, calling outer space the province of all mankind. This status as a common heritage of mankind has been used, though not without opposition, to enforce the right to access and shared use of outer space for all nations equally, particularly non-space-faring nations. It also prohibits the development of nuclear weapons in outer space. The treaty was passed by the United Nations General Assembly in 1963 and signed in 1967 by the USSR, the United States of America and the United Kingdom. As of 2017, 105 state parties have either ratified or acceded to the treaty. An additional 25 states signed the treaty, without ratifying it. Since 1958, outer space has been the subject of multiple United Nations resolutions. Of these, more than 50 have been concerning the international cooperation in the peaceful uses of outer space and preventing an arms race in space. 4 additional space law treaties have been negotiated and drafted by the UN's Committee on the Peaceful Uses of Outer Space. Still, there remains no legal prohibition against deploying conventional weapons in space, and anti-satellite weapons have been successfully tested by the US, USSR, China, And in 2019, India. The 1979 Moon Treaty turned the jurisdiction of all heavenly bodies, including the orbits around such bodies, over to the international community. The treaty has not been ratified by any nation that currently practices human spaceflight. In 1976, 8 equatorial states, Ecuador, Colombia, Brazil, Congo, Zaire, Uganda, Kenya, and Indonesia, met in Bogotá, Colombia. With their declaration of the first meeting of equatorial countries, or the Bogotá Declaration, they claimed control of the segment of the geosynchronous orbital path corresponding to each country. These claims are not internationally accepted. Ocean. The ocean, also the sea or the world ocean, is the body of salt water that covers approximately 70.8% of the surface of Earth and contains 97% of Earth's water. Another definition is any of the large bodies of water into which the Great Ocean is divided. Separate names are used to identify 5 different areas of the ocean: Pacific, the largest; Atlantic, Indian, Southern, Antarctic, and Arctic, the smallest. Seawater covers approximately 361 million square kilometers, 139 million square miles, of the planet. The ocean is the principal component of Earth's hydrosphere, and therefore integral to life on Earth. Acting as a huge heat reservoir, the ocean influences climate and weather patterns, the carbon cycle, and the water cycle. The ocean covers still 70% of the Earth, sometimes called the blue planet. Oceanographers divide the ocean into different vertical and horizontal zones based on physical and biological conditions. The pelagic zone consists of the water column from surface to ocean floor throughout the open ocean. The water column is further categorized in other zones depending on depth and on how much light is present. The photic zone includes water from the surface to a depth of 1% of the surface light, about 200 meters in the open ocean, where photosynthesis can occur. This makes the photic zone the most biodiverse. Photosynthesis by plants and microscopic algae, free-floating phytoplankton, creates organic matter using light, water, carbon dioxide, and nutrients. Ocean photosynthesis creates 50% of the oxygen in Earth's atmosphere. This upper sunlit zone is the origin of the food supply which sustains most of the ocean ecosystem. Light only penetrates to a depth of a few hundred meters. The remaining ocean below is cold and dark. The continental shelf where the ocean approaches dry land is more shallow, with a depth of a few hundred meters or less. Human activity has a greater impact on the continental shelf. Ocean temperatures depend on the amount of solar radiation reaching the ocean surface. In the tropics, surface temperatures can rise to over 30 degrees Celsius, 86 degrees Fahrenheit. Near the poles where sea ice forms, the temperature in equilibrium is about 2 degrees Celsius, 28 degrees Fahrenheit. Deep seawater temperature is between 2 degrees Celsius, 28 degrees Fahrenheit, and 5 degrees Celsius, 41 degrees Fahrenheit, in all parts of the ocean. Water continuously circulates in the oceans, creating ocean currents. These directed movements of seawater are generated by forces acting upon the water, including temperature differences, atmospheric circulation, wind, the Coriolis effect, and differences in salinity. Tidal currents originate from tides, while surface currents are caused by wind and waves. Major ocean currents include the Gulf Stream, Kuroshio Current, Agulhas Current, and Antarctic Circumpolar Current. Collectively, currents move enormous amounts of water and heat around the globe. This circulation significantly impacts global climate and the uptake and redistribution of pollutants such as carbon dioxide by moving these contaminants from the surface into the deep ocean. Ocean water contains large quantities of dissolved gases, including oxygen, carbon dioxide, and nitrogen. This gas exchange takes place at the ocean surface, and solubility depends on the temperature and salinity of the water. The increasing concentration of carbon dioxide in the atmosphere due to fossil fuel combustion leads to higher concentrations in ocean water, resulting in ocean acidification. The ocean provides society with important environmental services, including climate regulation. It also offers a means of trade and transport and access to food and other resources. Known to be the habitat of over 230,000 species, it may contain far more, perhaps over 2 million species. However, the ocean is subject to numerous environmental threats, including marine pollution, overfishing, ocean acidification and other effects of climate change. The continental shelf and coastal waters that are most influenced by human activity are especially vulnerable. Ocean and sea. The terms the ocean or the sea used without specification refer to the interconnected body of salt water covering the majority of the Earth's surface. It includes the Atlantic, Pacific, Indian, Southern, and Arctic Oceans. As a general term, the ocean is mostly interchangeable with the sea in American English, but not in British English. Strictly speaking, a sea is a body of water, generally a division of the world ocean, partly or fully enclosed by land. The word sea can also be used for many specific, much smaller bodies of seawater, such as the North Sea or the Red Sea. There is no sharp distinction between seas and oceans, though generally seas are smaller, and are often partly, as marginal seas, or wholly, as inland seas, bordered by land. World ocean. Further information: ocean current, thermohaline circulation, and ocean general circulation model. The contemporary concept of the world ocean was coined in the early 20th century by the Russian oceanographer Yuri Shopolsky to refer to the continuous ocean that covers and encircles most of Earth. The global, interconnected body of salt water is sometimes referred to as the world ocean or global ocean. The concept of a continuous body of water with relatively free interchange among its parts is of fundamental importance to oceanography. Ocean ridges and ocean basins. World distribution of mid-oceanic ridges, USGS. Every ocean basin has a mid-ocean ridge, which creates a long mountain range beneath the ocean. Together they form the global mid-oceanic ridge system that features the longest mountain range in the world. The longest continuous mountain range is 65,000 kilometers, 40,000 miles. This underwater mountain range is several times longer than the longest continental mountain range, the Andes. Oceanographers state that less than 20% of the oceans have been mapped. Formation. Main article: Origin of water on Earth. The origin of Earth's oceans is unknown. Oceans are thought to have formed in the Hadean and may have been the cause for the emergence of life. Scientists believe that a sizable quantity of water would have been in the material that formed the Earth. Water molecules would have escaped Earth's gravity more easily when it was less massive during its formation. This is called atmospheric escape. Plate tectonics, post-glacial rebound, and sea level rise continually change the coastline and structure of the world ocean. A global ocean has existed in one form or another on Earth for eons. Marine life. Main articles: marine life, marine habitat, marine primary production, marine biology, and marine ecosystem. Life within the ocean evolved 3 billion years prior to life on land. Both the depth and the distance from shore strongly influence the biodiversity of the plants and animals present in each region. The diversity of life in the ocean is immense, including animals. Most animal fauna have species that inhabit the ocean, including many that are only found in marine environments such as sponges, cnidaria, such as corals and jellyfish, comb jellies, brachiopods, and echinoderms, such as sea urchins and sea stars. Many other familiar animal groups primarily live in the ocean, including cephalopods, includes octopus and squid, crustaceans, includes lobsters, crabs, and shrimp, fish, sharks, cetaceans, includes whales, dolphins, and porpoises. In addition, many land animals have adapted to living a major part of their life on the oceans. For instance, seabirds are a diverse group of birds that have adapted to a life mainly on the oceans. They feed on marine animals and spend most of their lifetime on water, many only going on land for breeding. Other birds that have adapted to oceans as their living space are penguins, seagulls and pelicans. 7 species of turtles, the sea turtles, also spend most of their time in the oceans. Plants, including sea grasses, or mangroves. Algae. Algae is a catch-all term to include many photosynthetic, single-celled eukaryotes, such as green algae, diatoms, and dinoflagellates, but also multicellular algae, such as some red algae, including organisms like Pyropia, which is the source of the edible nori seaweed, and brown algae, including organisms like kelp. Bacteria, ubiquitous single-celled prokaryotes found throughout the world. Archaea, prokaryotes distinct from bacteria, that inhabit many environments of the ocean, as well as many extreme environments. Fungi, many marine fungi with diverse roles are found in oceanic environments. This section is an excerpt from Marine Life. Killer whales, orcas, are highly visible marine apex predators that hunt many large species. But most biological activity in the ocean takes place with microscopic marine organisms that cannot be seen individually with the naked eye, such as marine bacteria and phytoplankton. Marine life, sea life, or ocean life is the plants, animals and other organisms that live in the salt water of the sea or ocean, or the brackish water of coastal estuaries. At a fundamental level, marine life affects the nature of the planet. Marine organisms, mostly microorganisms, produce oxygen and sequester carbon. Marine life impart shape and protect shorelines, and some marine organisms even help create new land, for example coral-building reefs. Most life forms evolved initially in marine habitats. By volume, oceans provide about 90% of the living space on the planet. The earliest vertebrates appeared in the form of fish, which live exclusively in water. Some of these evolved into amphibians, which spend portions of their lives in water and portions on land. One group of amphibians evolved into reptiles and mammals, and a few subsets of each returned to the ocean as sea snakes, sea turtles, seals, manatees, and whales. Plant forms such as kelp and other algae grow in the water and are the basis for some underwater ecosystems. Plankton forms the general foundation of the ocean food chain, particularly phytoplankton, which are key primary producers. More than 200,000 marine species have been documented, and perhaps 2 million marine species are yet to be documented. Marine species range in size from the microscopic like phytoplankton, which can be as small as 0.02 micrometers, to huge cetaceans like the blue whale, the largest known animal, reaching 33 meters, 108 feet, in length. Marine microorganisms, including protists and bacteria and their associated viruses, have been variously estimated as constituting about 70% or about 90% of the total marine biomass. Marine life is studied scientifically in both the marine biology and in biological oceanography. The term marine comes from the Latin mare, meaning sea or ocean. This section is an excerpt from Marine Habitats. Coral reefs provide marine habitats for tube sponges, which in turn become marine habitats for fishes. Marine habitats are habitats that support marine life. Marine life depends in some way on the salt water that is in the sea. The term marine comes from the Latin mare, meaning sea or ocean. A habitat is an ecological or environmental area inhabited by one or more living species. The marine environment supports many kinds of these habitats. Marine habitats can be divided into coastal and open ocean habitats. Coastal habitats are found in the area that extends from as far as the tide comes in on the shoreline out to the edge of the continental shelf. Most marine life is found in coastal habitats, even though the shelf area occupies only 7% of the total ocean area. Open ocean habitats are found in the deep ocean beyond the edge of the continental shelf. This section is an excerpt from Marine Ecosystem. Coral reefs form complex marine ecosystems with tremendous biodiversity. Marine ecosystems are the largest diverse aquatic ecosystems and exist in waters that have a high salt content. These systems contrast with freshwater ecosystems, which have a lower salt content. Marine waters cover more than 70% of the surface of the Earth and account for more than 97% of Earth's water supply and 90% of habitable space on Earth. Seawater has an average salinity of 35 parts per thousand of water. Actual salinity varies among different marine ecosystems. Marine ecosystems can be divided into many zones depending upon water depth and shoreline features. The oceanic zone is the vast open part of the ocean where animals such as whales, sharks, and tuna live. The benthic zone consists of substrates below water where many invertebrates live. The intertidal zone is the area between high and low tides. Other nearshore, neritic zones can include mudflats, seagrass meadows, mangroves, rocky intertidal systems, salt marshes, coral reefs, lagoons. In the deep water, hydrothermal vents may occur where chemosynthetic sulfur bacteria form the base of the food web. Sun. The Sun is the star at the center of the solar system. It is a nearly perfect ball of hot plasma, heated to incandescence by nuclear fusion reactions in its core, radiating the energy mainly as visible light, ultraviolet light, and infrared radiation. It is by far the most important source of energy for life on Earth. Its diameter is about 1.39 million kilometers, 864,000 miles, or 109 times that of Earth. Its mass is about 330,000 times that of Earth, and it accounts for about 99.86% of the total mass of the solar system. Roughly 3/4 of the Sun's mass consists of hydrogen, 73%, the rest is mostly helium, 25%, with much smaller quantities of heavier elements, including oxygen, carbon, neon and iron. According to its spectral class, the Sun is a G-type main sequence star, G2V. As such, it is informally, and not completely accurately, referred to as a yellow dwarf. Its light is closer to white than yellow. It formed approximately 4.6 billion years ago from the gravitational collapse of matter within a region of a large molecular cloud. Most of this matter gathered in the center, whereas the rest flattened into an orbiting disk that became the solar system. The central mass became so hot and dense that it eventually initiated nuclear fusion in its core. It is thought that almost all stars form by this process. The Sun's core fuses about 600 million tons of hydrogen into helium every second, converting 4 million tons of matter into energy every second as a result. This energy, which can take between 10,000 and 170,000 years to escape the core, is the source of the Sun's light and heat. When hydrogen fusion in its core has diminished to the point at which the Sun is no longer in hydrostatic equilibrium, its core will undergo a marked increase in density and temperature while its outer layers expand, eventually transforming the Sun into a red giant. It is calculated that the Sun will become sufficiently large to engulf the current orbits of Mercury and Venus, and render Earth uninhabitable, but not for about 5 billion years. After this, it will shed its outer layers and become a dense type of cooling star known as a white dwarf, and no longer produce energy by fusion, but still glow and give off heat from its previous fusion. The enormous effect of the Sun on Earth has been recognized since prehistoric times. The Sun was thought of by some cultures as a deity. The synodic rotation of Earth and its orbit around the Sun are the basis of some solar calendars. The predominant calendar in use today is the Gregorian calendar, which is based upon the standard 16th century interpretation that the Sun's observed movement is primarily due to it actually moving. Composition. The Sun is composed primarily of the chemical elements hydrogen and helium. At this time in the Sun's life, they account for 74.9% and 23.8% of the mass of the Sun in the photosphere, respectively. All heavier elements, called metals in astronomy, account for less than 2% of the mass, with oxygen, roughly 1% of the Sun's mass, carbon, 0.3%, neon, 0.2%, and iron, 0.2%, being the most abundant. The Sun's original chemical composition was inherited from the interstellar medium out of which it formed. Originally it would have contained about 71.1% hydrogen, 27.4% helium, and 1.5% heavier elements. The hydrogen and most of the helium in the Sun would have been produced by Big Bang nucleosynthesis in the first 20 minutes of the universe, and the heavier elements were produced by previous generations of stars before the Sun was formed, and spread into the interstellar medium during the final stages of stellar life and by events such as supernovae. Since the Sun formed, the main fusion process has involved fusing hydrogen into helium. Over the past 4.6 billion years, the amount of helium and its location within the Sun has gradually changed. Within the core, the proportion of helium has increased from about 24% to about 60% due to fusion, and some of the helium and heavy elements have settled from the photosphere towards the center of the Sun because of gravity. The proportions of metals, heavier elements, is unchanged. Heat is transferred outward from the Sun's core by radiation rather than by convection. See radiative zone below, so the fusion products are not lifted outward by heat. They remain in the core, and gradually an inner core of helium has begun to form that cannot be fused because presently the Sun's core is not hot or dense enough to fuse helium. In the current photosphere, the helium fraction is reduced, and the metallicity is only 84% of what it was in the protostellar phase, before nuclear fusion in the core started. In the future, helium will continue to accumulate in the core, and in about 5 billion years this gradual buildup will eventually cause the Sun to exit the main sequence and become a red giant. The chemical composition of the photosphere is normally considered representative of the composition of the primordial solar system. The solar heavy element abundance is described above are typically measured both using spectroscopy of the Sun's photosphere and by measuring abundances in meteorites that have never been heated to melting temperatures. These meteorites are thought to retain the composition of the protostellar Sun and are thus not affected by the settling of heavy elements. The two methods generally agree well. Structure and fusion. The structure of the Sun contains the following layers. Core, the innermost 20 to 25% of the Sun's radius, where temperature and pressure are sufficient for nuclear fusion to occur. Hydrogen fuses into helium, which cannot itself be fused at this point in the Sun's life. The fusion process releases energy, and the core gradually becomes enriched in helium. Radiative zone, convection cannot occur until much nearer to the surface of the Sun. Therefore, between about 20 to 25% of the radius, and 70% of the radius, there is a radiative zone in which energy transfer occurs by means of radiation, photons, rather than by convection. Tachocline, the boundary region between the radiative and convective zones. Convective zone, between about 70% of the Sun's radius and a point close to the visible surface. The Sun is cool and diffuse enough for convection to occur, and this becomes the primary means of outward heat transfer, similar to weather cells which form in the Earth's atmosphere. Because the Sun is a gaseous object, it does not have a clearly defined surface. Its visible parts are usually divided into a photosphere and atmosphere. Photosphere, the deepest part of the Sun which we can directly observe with visible light. Atmosphere, a gaseous halo surrounding the Sun, comprising the chromosphere, solar transition region, corona and heliosphere. These can be seen when the main part of the Sun is hidden, for example, during a solar eclipse. Core. Main article, solar core. The core of the Sun extends from the center to about 20 to 25% of the solar radius. It has a density of up to 150 grams/cm3, about 150 times the density of water, and a temperature of close to 15.7 million kelvins. By contrast, the Sun's surface temperature is approximately 5,800 K. Recent analysis of SOHO mission data favors a faster rotation rate in the core than in the radiative zone above. Through most of the Sun's life, energy has been produced by nuclear fusion in the core region through a series of nuclear reactions called the PP, proton-proton, chain. This process converts hydrogen into helium. Only 0.8% of the energy generated in the Sun comes from another sequence of fusion reactions called the CNO cycle, though this proportion is expected to increase as the Sun becomes older. The core is the only region in the Sun that produces an appreciable amount of thermal energy through fusion. 99% of the power is generated within 24% of the Sun's radius, and by 30% of the radius, fusion has stopped nearly entirely. The remainder of the Sun is heated by this energy as it is transferred outwards through many successive layers, finally to the solar photosphere where it escapes into space through radiation, photons, or advection, massive particles. The proton-proton chain occurs around 9.2 *1037 times each second in the core, converting about 3.7 protons into alpha particles, helium nuclei, every second, out of a total of 8.9 free protons in the Sun, or about 6.2 1011 kilograms/s. Fusing 4 free protons, hydrogen nuclei, into a single alpha particle, helium nucleus, releases around 0.7% of the fused mass as energy, so the Sun releases energy at the mass-energy conversion rate of 4.26 million metric tons per second, which requires 600 metric megatons of hydrogen, for 384.6 yottawatts, 3.846 or 9.192 megatons of TNT per second. The large power output of the Sun is mainly due to the huge size and density of its core, compared to Earth and objects on Earth, with only a fairly small amount of power being generated per cubic meter. Theoretical models of the Sun's interior indicate maximum power density, or energy production, of approximately 276.5 watts per cubic meter at the center of the core, which is about the same power density inside a compost pile. The fusion rate in the core is in a self-correcting equilibrium. A slightly higher rate of fusion would cause the core to heat up more and expand slightly against the weight of the outer layers, reducing the density and hence the fusion rate and correcting the perturbation, and a slightly lower rate would cause the core to cool and shrink slightly, increasing the density and increasing the fusion rate and again reverting it to its present rate. Radiative zone. Main article, radiative zone. From the core out to about 0.7 solar radii, thermal radiation is the primary means of energy transfer. The temperature drops from approximately 7 million to 2 million kelvins with increasing distance from the core. This temperature gradient is less than the value of the adiabatic lapse rate and hence cannot drive convection, which explains why the transfer of energy through this zone is by radiation instead of thermal convection. Ions of hydrogen and helium emit photons, which travel only a brief distance before being reabsorbed by other ions. The density drops 100-fold, from 20 grams/cm3 to 0.2 grams/cm3, between 0.25 solar radii and 0.7 radii, the top of the radiative zone. Tachocline. Main article, tachocline. The radiative zone and the convective zone are separated by a transition layer, the tachocline. This is a region where the sharp regime change between the uniform rotation of the radiative zone and the differential rotation of the convection zone results in a large shear between the two, a condition where successive horizontal layers slide past one another. Presently, it is hypothesized, see solar dynamo, that a magnetic dynamo within this layer generates the Sun's magnetic field. Convective zone. Main article, convection zone. The Sun's convection zone extends from 0.7 solar radii, 500,000 kilometers, to near the surface. In this layer, the solar plasma is not dense enough or hot enough to transfer the heat energy of the interior outward via radiation. Instead, the density of the plasma is low enough to allow convective currents to develop and move the Sun's energy outward towards its surface. Material heated at the tachocline picks up heat and expands, thereby reducing its density and allowing it to rise. As a result, an orderly motion of the mass develops into thermal cells that carry the majority of the heat outward to the Sun's photosphere above. Once the material diffusively and radiatively cools just beneath the photospheric surface, its density increases, and it sinks to the base of the convection zone, where it again picks up heat from the top of the radiative zone and the convective cycle continues. At the photosphere, the temperature has dropped to 5,700 K and the density to only 0.2 grams/m3, about 1/10,000th the density of air at sea level. The thermal columns of the convection zone form an imprint on the surface of the Sun, giving it a granular appearance called the solar granulation at the smallest scale and supergranulation at larger scales. Turbulent convection in this outer part of the solar interior sustains small-scale dynamo action over the near-surface volume of the Sun. The Sun's thermal columns are Barnard cells and take the shape of roughly hexagonal prisms. Photosphere. Main article, Photosphere. The effective temperature, or black body temperature, of the Sun, 5,777 K, is the temperature a black body of the same size must have to yield the same total emissive power. A miasma of plasma. High-resolution image of the Sun's surface taken by the Daniel K. Inouye Solar Telescope, KIST. The visible surface of the Sun, the photosphere, is the layer below which the Sun becomes opaque to visible light. Photons produced in this layer escape the Sun through the transparent solar atmosphere above it and become solar radiation, sunlight. The change in opacity is due to the decreasing amount of H ions, which absorb visible light easily. Conversely, the visible light we see is produced as electrons react with hydrogen atoms to produce H ions. The photosphere is tens to hundreds of kilometers thick, and is slightly less opaque than air on Earth. Because the upper part of the photosphere is cooler than the lower part, an image of the Sun appears brighter in the center than on the edge or limb of the solar disk, in a phenomenon known as limb darkening. The spectrum of sunlight has approximately the spectrum of a black body radiating at 5,777 K, 5,504 degrees Celsius, 9,939 degrees Fahrenheit, interspersed with atomic absorption lines from the tenuous layers above the photosphere. The photosphere has a particle density of ~1023 meters (3), about 0.37% of the particle number per volume of Earth's atmosphere at sea level. The photosphere is not fully ionized. The extent of ionization is about 3%, leaving almost all of the hydrogen in atomic form. During early studies of the optical spectrum of the photosphere, some absorption lines were found that did not correspond to any chemical elements then known on Earth. In 1868, Norman Lockyer hypothesized that these absorption lines were caused by a new element that he dubbed helium, after the Greek sun god Helios. 25 years later, helium was isolated on Earth. Atmosphere. See also, stellar atmosphere. During a total solar eclipse, the solar corona can be seen with the naked eye, during the brief period of totality. During a total solar eclipse, when the disk of the Sun is covered by that of the Moon, parts of the Sun's surrounding atmosphere can be seen. It is composed of four distinct parts: the chromosphere, the transition region, the corona and the heliosphere. The coolest layer of the Sun is a temperature minimum region extending to about 500 kilometers above the photosphere, and has a temperature of about 4,100 K. This part of the Sun is cool enough to allow the existence of simple molecules such as carbon monoxide and water, which can be detected via their absorption spectra. The chromosphere, transition region, and corona are much hotter than the surface of the Sun. The reason is not well understood, but evidence suggests that Alfvén waves may have enough energy to heat the corona. Above the temperature minimum layer is a layer about 2,000 kilometers thick, dominated by a spectrum of emission and absorption lines. It is called the chromosphere from the Greek root chroma, meaning color, because the chromosphere is visible as a colored flash at the beginning and end of total solar eclipses. The temperature of the chromosphere increases gradually with altitude, ranging up to around 20,000 K near the top. In the upper part of the chromosphere, helium becomes partially ionized. Taken by Hinode's Solar Optical Telescope on January 12, 2007, this image of the Sun reveals the filamentary nature of the plasma connecting regions of different magnetic polarity. Above the chromosphere, in a thin, about 200 kilometers, transition region, the temperature rises rapidly from around 20,000 K in the upper chromosphere to coronal temperatures closer to 1 million K. The temperature increase is facilitated by the full ionization of helium in the transition region, which significantly reduces radiative cooling of the plasma. The transition region does not occur at a well-defined altitude. Rather, it forms a kind of nimbus around chromospheric features such as spicules and filaments, and is in constant, chaotic motion. The transition region is not easily visible from Earth's surface, but is readily observable from space by instruments sensitive to the extreme ultraviolet portion of the spectrum. The corona is the next layer of the Sun. The low corona, near the surface of the Sun, has a particle density around 1015 meters (3 to 1016 meters (3). G. The average temperature of the corona and solar wind is about 1 million to 2 million K. However, in the hottest regions it is 8 million to 20 million K. Although no complete theory yet exists to account for the temperature of the corona, at least some of its heat is known to be from magnetic reconnection. The corona is the extended atmosphere of the Sun, which has a volume much larger than the volume enclosed by the Sun's photosphere. A flow of plasma outward from the Sun into interplanetary space is the solar wind. The heliosphere, the tenuous outermost atmosphere of the Sun, is filled with the solar wind plasma. This outermost layer of the Sun is defined to begin at the distance where the flow of the solar wind becomes supergalvanic, that is, where the flow becomes faster than the speed of all vane waves, at approximately 20 solar radii, 0.1 astronomical units. Turbulence and dynamic forces in the heliosphere cannot affect the shape of the solar corona within, because the information can only travel at the speed of all vane waves. The solar wind travels outward continuously through the heliosphere, forming the solar magnetic field into a spiral shape, until it impacts the heliopause more than 50 astronomical units from the Sun. In December 2004, the Voyager 1 probe passed through a shock front that is thought to be part of the heliopause. In late 2012, Voyager 1 recorded a marked increase in cosmic ray collisions and a sharp drop in lower energy particles from the solar wind, which suggested that the probe had passed through the heliopause and entered the interstellar medium, and indeed did so August 25, 2012 at approximately 122 astronomical units from the Sun. The heliosphere has a heliotail which stretches out behind it due to the Sun's movement. Photons and neutrinos. See also, solar irradiance. High-energy gamma-ray photons initially released with fusion reactions in the core are almost immediately absorbed by the solar plasma of the radiative zone, usually after traveling only a few millimeters. Re-emission happens in a random direction and usually at slightly lower energy. With this sequence of emissions and absorptions, it takes a long time for radiation to reach the Sun's surface. Estimates of the photon travel time range between 10,000 and 170,000 years. In contrast, it takes only 2.3 seconds for the neutrinos, which account for about 2% of the total energy production of the Sun, to reach the surface. Because energy transport in the Sun is a process that involves photons in thermodynamic equilibrium with matter, the timescale of energy transport in the Sun is longer, on the order of 30 million years. This is the time it would take the Sun to return to a stable state if the rate of energy generation in its core were suddenly changed. Neutrinos are also released by the fusion reactions in the core, but, unlike photons, they rarely interact with matter, so almost all are able to escape the Sun immediately. For many years measurements of the number of neutrinos produced in the Sun were lower than theories predicted by a factor of 3. This discrepancy was resolved in 2001 through the discovery of the effects of neutrino oscillation. The Sun emits the number of neutrinos predicted by the theory, but neutrino detectors were missing 2/3 of them because the neutrinos had changed flavor by the time they were detected. Galactic location. Main article, Solar System section, Galactic context. Illustration of the Milky Way, showing the location of the Sun. The radial coordinates shown, radiating lines, are centered on the Sun's location, labeled. The Sun lies close to the inner rim of the Milky Way's Orion arm, in the local interstellar cloud or the Gould belt, at a distance of 7.5 to 8.5 kiloparsecs, 24 to 28 kilolight-years, from the galactic center. The Sun is contained within the local bubble, a space of rarefied hot gas, possibly produced by the supernova remnant gemming or multiple supernovae in subgroup B1 of the Pleiades moving group. The distance between the local arm and the next arm out, the Perseus arm, is about 6,500 light-years. The Sun, and thus the Solar System, is found in what scientists call the galactic habitable zone. The apex of the Sun's way, or the solar apex, is the direction that the Sun travels relative to other nearby stars. This motion is towards a point in the constellation Hercules, near the star Vega. Stars within 100 parsecs of the Sun, 326 light-years, have speeds relative to the Sun which can be modeled approximately by a Maxwell-Boltzmann distribution, especially for the lower speeds, or a log-normal distribution, especially for the higher speeds, but with more high-speed stars, greater than 300 kilometers per second, than predicted by either distribution. The mean velocity of these stars, not the mean speed, relative to the Sun, or the mean velocity of the Sun relative to them, is around 20 kilometers per second. Within 32.6 light-years of the Sun there are 315 known stars in 227 systems, as of 2000, including 163 single stars. It is estimated that a further 130 systems within this range have not yet been identified. Out to 81.5 light-years, there may be up to 7,500 stars, of which around 2,600 are known. The number of substellar objects in that volume are expected to be comparable to the number of stars. Of the 50 nearest stellar systems within 17 light-years from Earth, the closest being the red dwarf Proxima Centauri at approximately 4.2 light-years, the Sun ranks fourth in mass. The Gaia catalogue of nearby stars, all within 100 parsecs, contains 331,312 stars and is thought to include at least 92% of the stars of stellar spectral type M9 or earlier, i.e. hotter. Solar System. The Solar System C is the gravitationally bound system of the Sun and the objects that orbit it. Of the bodies that orbit the Sun directly, the largest are the 4 gas and ice giants and the 4 terrestrial planets, followed by an unknown number of dwarf planets and innumerable small solar system bodies. Of the bodies that orbit the Sun indirectly, the natural satellites, 2 are larger than Mercury, the smallest terrestrial planet, and 1 is nearly as large. D. The Solar System formed 4.6 billion years ago from the gravitational collapse of a giant interstellar molecular cloud. The vast majority of the system's mass is in the Sun, with the majority of the remaining mass contained in Jupiter. The 4 inner system planets, Mercury, Venus, Earth and Mars, are terrestrial planets, being composed primarily of rock and metal. The 4 giant planets of the outer system are substantially more massive than the terrestrials. The 2 largest planets, Jupiter and Saturn, are gas giants, being composed mainly of hydrogen and helium. The next 2, Uranus and Neptune, are ice giants, being composed mostly of substances with relatively high melting points compared with hydrogen and helium, called volatiles, such as water, ammonia and methane. All 8 have nearly circular orbits that lie close to the plane of the Earth's orbit, called the ecliptic. The Solar System also contains smaller objects. 6 of the major planets, the 6 largest possible dwarf planets, and many of the smaller bodies are orbited by natural satellites, commonly called moons after the Moon. Each of the giant planets and some smaller bodies are encircled by planetary rings of ice, dust and moonlets. The asteroid belt, which lies between the orbits of Mars and Jupiter, contains objects composed of rock, metal and ice. Beyond Neptune's orbit lie the Kuiper belt and scatter disk, which are populations of objects composed mostly of ice and rock. Beyond them lies a class of minor planets called detached objects. Within these populations, some objects are large enough to have rounded under their own gravity and thus to be planets under some definitions, though there is considerable debate as to how many such objects there will prove to be. Such objects are categorized as dwarf planets. Astronomers generally accept about 9 objects as dwarf planets: the asteroid series, the Kuiper belt objects Pluto, Orcus, Haumea, Quaoar, and Makemake, the scatter disk objects Gongon and Eris, and Sedna. Various small body populations, including comets, centaurs and interplanetary dust clouds, freely travel between the regions of the Solar System. The solar wind, a stream of charged particles flowing outwards from the Sun, creates a bubble-like region of interplanetary medium in the interstellar medium known as the heliosphere. The heliopause is the point at which pressure from the solar wind is equal to the opposing pressure of the interstellar medium. It extends out to the edge of the scatter disk. The Oort cloud, which is thought to be the source for long-period comets, may also exist at a distance roughly 1,000 times further than the heliosphere. The Solar System is located 26,000 light-years from the center of the Milky Way galaxy and the Orion Arm, which contains most of the visible stars in the night sky. The nearest stars are within the so-called local bubble, with the closest, Proxima Centauri, at 4.25 light-years. Inner Solar System. Overview of the Inner Solar System up to the Jovian System. The Inner Solar System is the region comprising the terrestrial planets and the asteroid belt. Composed mainly of silicates and metals, 83, the objects of the Inner Solar System are relatively close to the Sun. The radius of this entire region is less than the distance between the orbits of Jupiter and Saturn. This region is also within the frost line, which is a little less than 5 astronomical units, 750 million kilometer, 460 million mile, from the Sun. Inner planets. Main article, terrestrial planet. The terrestrial planets of the Solar System, Mercury, Venus, Earth, and Mars, size to scale. The 4 terrestrial or inner planets have dense, rocky compositions, few or no moons, and no ring systems. They are composed largely of refractory minerals such as the silicates, which form their crusts and mantles, and metals such as iron and nickel which form their cores. 3 of the 4 inner planets, Venus, Earth and Mars, have atmospheres substantial enough to generate weather. All have impact craters and tectonic surface features, such as rift valleys and volcanoes. The term inner planet should not be confused with inferior planet, which designates those planets that are closer to the Sun than Earth is, i.e. Mercury and Venus. Mercury. Main article, Mercury, planet. Mercury, 0.4 astronomical units, 60 million kilometer, 37 million mile, from the Sun, is the closest planet to the Sun. The smallest planet in the Solar System, 0.055 Earth, Mercury has no natural satellites. The dominant geological features are impact craters or basins with the ejectablancates, the remains of early volcanic activity including magma flows, and low ridges or roops that were probably produced by a period of contraction early in the planet's history. Mercury's very tenuous atmosphere consists of solar wind particles trapped by Mercury's magnetic field, as well as atoms blasted off its surface by the solar wind. Its relatively large iron core and thin mantle have not yet been adequately explained. Hypotheses include that its outer layers were stripped off by a giant impact, or that it was prevented from fully accreting by the young sun's energy. There have been searches for volcanoids, asteroids in stable orbits between Mercury and the Sun, but none have been discovered. Venus. Main article, Venus. Venus, 0.7 astronomical units, 100 million kilometer, 65 million mile, from the Sun, is close in size to Earth, 0.815 Earth, and, like Earth, has a thick silicate mantle around an iron core, a substantial atmosphere, and evidence of internal geological activity. It is much drier than Earth, and its atmosphere is 90 times as dense. Venus has no natural satellites. It is the hottest planet, with surface temperatures over 400 degrees Celsius, 752 degrees Fahrenheit, mainly due to the amount of greenhouse gases in the atmosphere. The planet has no magnetic field that would prevent depletion of its substantial atmosphere, which suggests that its atmosphere is being replenished by volcanic eruptions. A relatively young planetary surface displays extensive evidence of volcanic activity, but is devoid of plate tectonics. It may undergo resurfacing episodes on a timescale of 700 million years. Earth. Main article, Earth. Earth, 1 astronomical unit, 150 million kilometer, 93 million mile, from the Sun, is the largest and densest of the inner planets, the only one known to have current geological activity, and the only place where life is known to exist. Its liquid hydrosphere is unique among the terrestrial planets, and it is the only planet where plate tectonics has been observed. Earth's atmosphere is radically different from those of the other planets, having been altered by the presence of life to contain 21% free oxygen. The planetary magnetosphere shields the surface from solar and cosmic radiation, limiting atmospheric stripping and maintaining habitability. It has one natural satellite, the Moon, the only large satellite of a terrestrial planet in the solar system. Mars. Main article, Mars. Mars, 1.5 astronomical units, 220 million kilometer, 140 million mile, from the Sun, is smaller than Earth and Venus, 0.107 Earth. It has an atmosphere of mostly carbon dioxide with the surface pressure of 6.1 millibars, 0.088 pounds per square inch, 0.18 inches of mercury, roughly 0.6% of that of Earth but sufficient to support weather phenomena. Its surface, peppered with volcanoes, such as Olympus Mons, and rift valleys, such as Valles Marineris, shows geological activity that may have persisted until as recently as 2 million years ago. Its red color comes from iron oxide, rust, in its soil. Mars has two tiny natural satellites, Deimos and Phobos, thought to be either captured asteroids, or rejected debris from a massive impact early in Mars's history. Asteroids, except for the largest, Ceres, are classified as small solar system bodies E, and are composed mainly of refractory rocky and metallic minerals, with some ice. They range from a few meters to hundreds of kilometers in size. Asteroids smaller than 1 meter are usually called meteoroids and micrometeoroids, grain-sized, with the exact division between the two categories being debated over the years. As of 2017, the IAA designates asteroids having diameter between about 30 micrometers and 1 meter as micrometeoroids, and terms smaller particles dust. The asteroid belt occupies the orbit between Mars and Jupiter, between 2.3 and 3.3 astronomical units, 340 and 490 million kilometer, 210 and 310 million mile, from the Sun. It is thought to be remnants from the solar system's formation that failed to coalesce because of the gravitational interference of Jupiter. The asteroid belt contains tens of thousands, possibly millions, of objects over 1 kilometer in diameter. Despite this, the total mass of the asteroid belt is unlikely to be more than 1,000th of that of Earth. The asteroid belt is very sparsely populated, spacecraft routinely pass through without incident. Ceres. Main article, Ceres, dwarf planet. Ceres, 2.77 astronomical units, 414 million kilometer, 257 million mile, from the Sun, is the largest asteroid, a protoplanet, and a dwarf planet. It has a diameter of slightly under 1,000 kilometers, 620 miles, and a mass large enough for its own gravity to pull it into a spherical shape. Ceres was considered a planet when it was discovered in 1801, but as further observations revealed additional asteroids, it became common to consider it as one of the minor rather than major planets. It was then reclassified again as a dwarf planet in 2006 when the IAA definition of planet was established. Pallas and Vesta. Main articles, 2 Pallas and 4 Vesta. Pallas, 2.77 astronomical units from the Sun, and Vesta, 2.36 astronomical units from the Sun, are the largest asteroids in the asteroid belt, after Ceres. They are the other two protoplanets that survive more or less intact. At about 520 kilometers, 320 miles, in diameter, they were large enough to have developed planetary geology in the past, but both have suffered large impacts and been battered out of being round. Fragments from impacts upon these two bodies survive elsewhere in the asteroid belt, as the Pallas family and Vesta family. Both were considered planets upon their discoveries in 1802 and 1807 respectively, and then like Ceres generally considered as minor planets with the discovery of more asteroids. Some authors today have begun to consider Pallas and Vesta as planets again, along with Ceres, under geophysical definitions of the term. Asteroid groups. Asteroids in the asteroid belt are divided into asteroid groups and families based on their orbital characteristics. Kirkwood gaps are sharp dips in the distribution of asteroid orbits that correspond to orbital resonances with Jupiter. Asteroid moons are asteroids that orbit larger asteroids. They are not as clearly distinguished as planetary moons, sometimes being almost as large as their partners, for example that of 90 Antiope. The asteroid belt includes main belt comets, which may have been the source of Earth's water. Jupiter Trojans are located in either of Jupiter's L4 or L5 points, gravitationally stable regions leading and trailing a planet in its orbit. The term Trojan is also used for small bodies in any other planetary or satellite Lagrange point. Hilda asteroids are in a 2 to 3 resonance with Jupiter, that is, they go around the Sun 3 times for every 2 Jupiter orbits. The inner solar system contains near-Earth asteroids, many of which cross the orbits of the inner planets. Some of them are potentially hazardous objects. Outer solar system. Plot of objects around the Kuiper belt and other asteroid populations. The J, S, U and then denotes Jupiter, Saturn, Uranus, and Neptune. The outer region of the solar system is home to the giant planets and their large moons. The Centaurs and many short-period comets also orbit in this region. Due to their greater distance from the Sun, the solid objects in the outer solar system contain a higher proportion of volatiles, such as water, ammonia, and methane than those of the inner solar system because the lower temperatures allow these compounds to remain solid. Outer planets. Main article, giant planet. The outer planets Jupiter, Saturn, Uranus, and Neptune, compared to the inner planets Earth, Venus, Mars and Mercury at the bottom right. The 4 outer planets, also called giant planets or Jovian planets, collectively make up 99% of the mass known to orbit the Sun. AF. Jupiter and Saturn are together more than 400 times the mass of Earth and consist overwhelmingly of the gases hydrogen and helium, hence their designation as gas giants. Uranus and Neptune are far less massive, less than 20 Earth masses, each, and are composed primarily of ices. For these reasons, some astronomers suggest they belong in their own category, ice giants. All 4 giant planets have rings, although only Saturn's ring system is easily observed from Earth. The term superior planet designates planets outside Earth's orbit and thus includes both the outer planets and Mars. The ring moon systems of Jupiter, Saturn, and Uranus are like miniature versions of the solar system. That of Neptune is significantly different, having been disrupted by the capture of its largest moon Triton. Jupiter. Main article, Jupiter. Jupiter, 5.2 astronomical units, 780 million kilometer, 480 million mile, from the Sun, at 318 Earth, is 2.5 times the mass of all the other planets put together. It is composed largely of hydrogen and helium. Jupiter's strong internal heat creates semi-permanent features in its atmosphere, such as cloud bands and the Great Red Spot. The planet possesses a 4.2 to 14 Gauss-strength magnetosphere that spans 22 to 29 million kilometer, making it, in certain respects, the largest object in the solar system. Jupiter has 80 known satellites. The 4 largest, Ganymede, Callisto, Io, and Europa, are called the Galilean moons. They show similarities to the terrestrial planets, such as volcanism and internal heating. Ganymede, the largest satellite in the solar system, is larger than Mercury. Callisto is almost as large. Saturn. Main article, Saturn. Saturn, 9.5 astronomical units, 1.42 billion kilometer, 880 million mile, from the Sun, distinguished by its extensive ring system, has several similarities to Jupiter, such as its atmospheric composition and magnetosphere. Although Saturn has 60% of Jupiter's volume, it is less than a third as massive, at 95 Earth. Saturn is the only planet of the solar system that is less dense than water. The rings of Saturn are made up of small ice and rock particles. Saturn has 83 confirmed satellites composed largely of ice. 2 of these, Titan and Enceladus, show signs of geological activity. They, as well as 5 other Saturnian moons, Iapetus, Rhea, Dion, Tethys, and Mimas, are large enough to be round. Titan, the second largest moon in the solar system, is bigger than Mercury and the only satellite in the solar system to have a substantial atmosphere. Uranus. Main article, Uranus. Uranus, 19.2 astronomical units, 2.87 billion kilometer, 1.78 billion mile, from the Sun, at 14 Earth, has the lowest mass of the outer planets. Uniquely among the planets, it orbits the Sun on its side. Its axial tilt is over 90 degrees to the ecliptic. This gives the planet extreme seasonal variation as each pole points toward and then away from the Sun. It has a much colder core than the other giant planets and radiates very little heat into space. As a consequence, it has the coldest planetary atmosphere in the solar system. Uranus has 27 known satellites, the largest ones being Titania, Oberon, Umbriel, Ariel, and Miranda. Like the other giant planets, it also possesses a ring system and magnetosphere. Neptune. Main article, Neptune. Neptune, 30.1 astronomical units, 4.50 billion kilometer, 2.80 billion mile, from the Sun, though slightly smaller than Uranus, is more massive, 17 Earth, and hence more dense. It radiates more internal heat than Uranus, but not as much as Jupiter or Saturn. Neptune has 14 known satellites. The largest, Triton, is geologically active, with geysers of liquid nitrogen. Triton is the only large satellite with the retrograde orbit, which indicates that it did not form with Neptune, but was probably captured from the Kuiper belt. Neptune is accompanied in its orbit by several minor planets, termed Neptune Trojans, that either lead or trail the planet by about 1/6 of the way around the Sun, positions known as Lagrange points. Centaurs. Main article, Centaur, small solar system body. The Centaurs are icy comet-like bodies whose orbits have semi-major axes greater than Jupiter's, 5.5 astronomical units, 820 million kilometer, 510 million mile, and less than Neptune's, 30 astronomical units, 4.5 billion kilometer, 2.8 billion mile. The largest known Centaur, 10,199 Chiriclo, has a diameter of about 250 kilometers, 160 miles. The first Centaur discovered, 2060 Chiron, has also been classified as a comet, 95P, because it develops a coma just as comets do when they approach the Sun. Moon. The Moon is Earth's only natural satellite. At about 1/4 the diameter of Earth, comparable to the width of Australia, it is the fifth largest satellite in the solar system, the largest satellite in the solar system relative to its major planet, F, and larger than any known dwarf planet. The Moon is a planetary mass object that formed a differentiated rocky body, making it a satellite planet under the geophysical definitions of the term. It lacks any significant atmosphere, hydrosphere, or magnetic field. Its surface gravity is about 1/6 of Earth's, 0.1654 grams. Jupiter's moon Io is the only satellite in the solar system known to have a higher surface gravity and density. Orbiting Earth at an average distance of 384,400 kilometers, 238,900 miles, or about 30 times Earth's diameter, its gravitational influence very slowly lengthens Earth's day and is the main driver of Earth's tides. The Moon's orbit around Earth has a sidereal period of 27.3 days. During each synodic period of 29.5 days, the amount of visible surface illuminated by the Sun varies from 9 up to 100%, resulting in lunar phases that form the basis for the months of a lunar calendar. The Moon is tidally locked to Earth, which means that the length of a full rotation of the Moon on its own axis causes its same side, the near side, to always face Earth, and the somewhat longer lunar day is the same as the synodic period. That said, 59% of the total lunar surface can be seen from Earth through shifts in perspective due to libration. The most widely accepted origin explanation posits that the Moon formed 4.51 billion years ago, not long after Earth, out of the debris from a giant impact between the planet and a hypothesized Mars-sized body called Ea. It then receded to a wider orbit because of tidal interaction with the Earth. The near side of the Moon is marked by dark volcanic maria, seas, which fill the spaces between bright ancient crustal highlands and prominent impact craters. Most of the large impact basins and mirror surfaces were in place by the end of the Cambrian period, some 3 billion years ago. The lunar surface is relatively non-reflective, with a reflectance just slightly brighter than that of worn asphalt. However, because it has a large angular diameter, the full moon is the brightest celestial object in the night sky. The moon's apparent size is nearly the same as that of the sun, allowing it to cover the sun almost completely during a total solar eclipse. Both the moon's prominence in the earthly sky and its regular cycle of phases have provided cultural references and influences for human societies throughout history. Such influences can be found in language, calendar systems, art, and mythology. The first artificial object to reach the moon was the Soviet Union's Luna 2 uncrewed spacecraft in 1959. This was followed by the first successful soft landing by Luna 9 in 1966. The only human lunar missions to date have been those of the United States Apollo program, which landed 12 men on the surface between 1969 and 1972. These and later uncrewed missions returned lunar rocks that have been used to develop a detailed geological understanding of the moon's origins, internal structure, and subsequent history. Electricity. Electricity is the set of physical phenomena associated with the presence and motion of matter that has a property of electric charge. Electricity is related to magnetism, both being part of the phenomenon of electromagnetism, as described by Maxwell's equations. Various common phenomena are related to electricity, including lighting, static electricity, electric heating, electric discharges, and many others. The presence of an electric charge, which can be either positive or negative, produces an electric field. The movement of electric charges is an electric current and produces a magnetic field. When a charge is placed in a location with a non-zero electric field, a force will act on it. The magnitude of this force is given by Coulomb's law. If the charge moves, the electric field would be doing work on the electric charge. Thus we can speak of electric potential at a certain point in space, which is equal to the work done by an external agent in carrying a unit of positive charge from an arbitrarily chosen reference point to that point without any acceleration, and is typically measured in volts. Electricity is at the heart of many modern technologies, being used for electric power, where electric current is used to energize equipment. Electronics, which deals with electrical circuits that involve active electrical components such as vacuum tubes, transistors, diodes, and integrated circuits, and associated passive interconnection technologies. Electrical phenomena have been studied since antiquity, though progress in theoretical understanding remained slow until the 17th and 18th centuries. The theory of electromagnetism was developed in the 19th century, and by the end of that century electricity was being put to industrial and residential use by electrical engineers. The rapid expansion in electrical technology at this time transformed industry and society, becoming a driving force for the Second Industrial Revolution. Electricity's extraordinary versatility means it can be put to an almost limitless set of applications, which include transport, heating, lighting, communications, and computation. Electrical power is now the backbone of modern industrial society. Electric charge. The presence of charge gives rise to an electrostatic force. Charges exert a force on each other, an effect that was known, though not understood, in antiquity. A lightweight ball suspended from a string can be charged by touching it with a glass rod that has itself been charged by rubbing with a cloth. If a similar ball is charged by the same glass rod, it is found to repel the first. The charge acts to force the two balls apart. Two balls that are charged with a rubbed amber rod also repel each other. However, if one ball is charged by the glass rod, and the other by an amber rod, the two balls are found to attract each other. These phenomena were investigated in the late 18th century by Charles Augustin de Coulomb, who deduced that charge manifests itself in two opposing forms. This discovery led to the well-known axiom, like charged objects repel and opposite charged objects attract. The force acts on the charged particles themselves, hence charge has a tendency to spread itself as evenly as possible over a conducting surface. The magnitude of the electromagnetic force, whether attractive or repulsive, is given by Coulomb's law, which relates the force to the product of the charges and has an inverse square relation to the distance between them. The electromagnetic force is very strong, second only in strength to the strong interaction, but unlike that force it operates over all distances. In comparison with the much weaker gravitational force, the electromagnetic force pushing two electrons apart is 1042 times that of the gravitational attraction pulling them together. Charge originates from certain types of subatomic particles, the most familiar carriers of which are the electron and proton. Electric charge gives rise to and interacts with the electromagnetic force, one of the four fundamental forces of nature. Experiment has shown charge to be a conserved quantity, that is, the net charge within an electrically isolated system will always remain constant regardless of any changes taking place within that system. Within the system, charge may be transferred between bodies, either by direct contact, or by passing along a conducting material, such as a wire. The informal term static electricity refers to the net presence, or imbalance, of charge on a body, usually caused when dissimilar materials are rubbed together, transferring charge from one to the other. The charge on electrons and protons is opposite in sign, hence an amount of charge may be expressed as being either negative or positive. By convention, the charge carried by electrons is deemed negative, and that by protons positive, a custom that originated with the work of Benjamin Franklin. The amount of charge is usually given the symbol Q and expressed in coulombs. Each electron carries the same charge of approximately 1.6022 coulomb. The proton has a charge that is equivalent opposite, and thus plus 1.6022 coulomb. Charge is possessed not just by matter, but also by antimatter, each antiparticle bearing an equivalent opposite charge to its corresponding particle. Charge can be measured by a number of means, an early instrument being the gold leaf electroscope, which although still in use for classroom demonstrations, has been superseded by the electronic electrometer. Electric current. Main article, electric current. The movement of electric charge is known as an electric current, the intensity of which is usually measured in amperes. Current can consist of any moving charged particles, most commonly these are electrons, but any charge in motion constitutes a current. Electric current can flow through some things, electrical conductors, but will not flow through an electrical insulator. By historical convention, a positive current is defined as having the same direction of flow as any positive charge it contains, or to flow from the most positive part of a circuit to the most negative part. Current defined in this manner is called conventional current. The motion of negatively charged electrons around an electric circuit, one of the most familiar forms of current, is thus deemed positive in the opposite direction to that of the electrons. However, depending on the conditions, an electric current can consist of a flow of charged particles in either direction, or even in both directions at once. The positive to negative convention is widely used to simplify this situation. Two metal wires form an inverted V shape. A blindingly bright orange-white electric arc flows between their tips. An electric arc provides an energetic demonstration of electric current. The process by which electric current passes through a material is termed electrical conduction, and its nature varies with that of the charged particles and the material through which they are traveling. Examples of electric currents include metallic conduction, where electrons flow through a conductor such as metal, and electrolysis, where ions, charged atoms, flow through liquids, or through plasmas such as electrical sparks. While the particles themselves can move quite slowly, sometimes with an average drift velocity only fractions of a millimeter per second, the electric field that drives them itself propagates at close to the speed of light, enabling electrical signals to pass rapidly along wires. Current causes several observable effects, which historically were the means of recognizing its presence. That water could be decomposed by the current from a voltaic pile was discovered by Nicholson and Carlisle in 1800, a process now known as electrolysis. Their work was greatly expanded upon by Michael Faraday in 1833. Current through a resistance causes localized heating, an effect James Prescott Joule studied mathematically in 1840. One of the most important discoveries relating to current was made accidentally by Hans Christian Ørsted in 1820, when, while preparing a lecture, he witnessed the current in a wire disturbing the needle of a magnetic compass. He had discovered electromagnetism, a fundamental interaction between electricity and magnetics. The level of electromagnetic emissions generated by electric arcing is high enough to produce electromagnetic interference, which can be detrimental to the workings of adjacent equipment. In engineering or household applications, current is often described as being either direct current, DC, or alternating current, AC. These terms refer to how the current varies in time. Direct current, as produced by example from a battery and required by most electronic devices, is a unidirectional flow from the positive part of a circuit to the negative. If, as is most common, this flow is carried by electrons, they will be traveling in the opposite direction. Alternating current is any current that reverses direction repeatedly, almost always this takes the form of a sine wave. Alternating current thus pulses back and forth within a conductor without the charge moving any net distance over time. The time-averaged value of an alternating current is zero, but it delivers energy in first one direction, and then the reverse. Alternating current is affected by electrical properties that are not observed under steady-state direct current, such as inductance and capacitance. These properties, however, can become important when circuitry is subjected to transients, such as when first energized. Electric field. Main article, Electric field. See also, Electrostatics. The concept of the electric field was introduced by Michael Faraday. An electric field is created by a charged body in the space that surrounds it, and results in a force exerted on any other charges placed within the field. The electric field acts between two charges in a similar manner to the way that the gravitational field acts between two masses, and like it, extends towards infinity and shows an inverse square relationship with distance. However, there is an important difference. Gravity always acts in attraction, drawing two masses together, while the electric field can result in either attraction or repulsion. Since large bodies such as planets generally carry no net charge, the electric field at a distance is usually zero. Thus gravity is the dominant force at distance in the universe, despite being much weaker. Field lines emanating from a positive charge above a plane conductor. An electric field generally varies in space, and its strength at any one point is defined as the force, per unit charge, that would be felt by a stationary, negligible charge if placed at that point. The conceptual charge, termed a test charge, must be vanishingly small to prevent its own electric field disturbing the main field and must also be stationary to prevent the effect of magnetic fields. As the electric field is defined in terms of force, and force is a vector, having both magnitude and direction, so it follows that an electric field is a vector field. The study of electric fields created by stationary charges is called electrostatics. The field may be visualized by a set of imaginary lines whose direction at any point is the same as that of the field. This concept was introduced by Faraday, whose term lines of force still sometimes sees use. The field lines are the paths that a point positive charge would seek to make as it was forced to move within the field. They are however an imaginary concept with no physical existence, and the field permeates all the intervening space between the lines. Field lines emanating from stationary charges have several key properties. First, that they originate at positive charges and terminate at negative charges. Second, that they must enter any good conductor at right angles. And third, that they may never cross nor close in on themselves. A hollow conducting body carries all its charge on its outer surface. The field is therefore zero at all places inside the body. This is the operating principle of the Faraday cage, a conducting metal shell which isolates its interior from outside electrical effects. The principles of electrostatics are important when designing items of high-voltage equipment. There is a finite limit to the electric field strength that may be withstood by any medium. Beyond this point, electrical breakdown occurs and an electric arc causes flashover between the charged parts. Air, for example, tends to arc across small gaps at electric field strengths which exceed 30 kV per centimeter. Over larger gaps, its breakdown strength is weaker, perhaps 1 kV per centimeter. The most visible natural occurrence of this is lightning, caused when charge becomes separated into clouds by rising columns of air, and raises the electric field in the air to greater than it can withstand. The voltage of a large lightning cloud may be as high as 100 megavolts and have discharge energies as great as 250 kilowatt-hours. The field strength is greatly affected by nearby conducting objects, and it is particularly intense when it is forced to curve around sharply pointed objects. This principle is exploited in the lightning conductor, the sharp spike of which acts to encourage the lightning stroke to develop there, rather than to the building it serves to protect. Electric potential. Main article, electric potential. See also, voltage in battery, electricity. Two AA batteries each have a plus sign marked at one end. A pair of AA cells. The plus sign indicates the polarity of the potential difference between the battery terminals. The concept of electric potential is closely linked to that of the electric field. A small charge placed within an electric field experiences a force, and to have brought that charge to that point against the force requires work. The electric potential at any point is defined as the energy required to bring a unit test charge from an infinite distance slowly to that point. It is usually measured in volts, and 1 volt is the potential for which 1 joule of work must be expended to bring a charge of 1 coulomb from infinity. This definition of potential, while formal, has little practical application, and a more useful concept is that of electric potential difference, and is the energy required to move a unit charge between two specified points. An electric field has the special property that it is conservative, which means that the path taken by the test charge is irrelevant. All paths between two specified points expend the same energy, and thus a unique value for potential difference may be stated. The volt is so strongly identified as the unit of the choice for measurement and description of electric potential difference that the term voltage sees greater everyday usage. For practical purposes, it is useful to define a common reference point to which potentials may be expressed and compared. While this could be at infinity, a much more useful reference is the Earth itself, which is assumed to be at the same potential everywhere. This reference point naturally takes the name Earth or ground. Earth is assumed to be an infinite source of equal amounts of positive and negative charge, and is therefore electrically uncharged, and unchargeable. Electric potential is a scalar quantity, that is, it has only magnitude and not direction. It may be viewed as analogous to height, just as a released object will fall through a difference in heights caused by a gravitational field, so a charge will fall across the voltage caused by an electric field. As relief maps show contour lines marking points of equal height, a set of lines marking points of equal potential, known as equipotentials, may be drawn around an electrostatically charged object. The equipotentials cross all lines of force at right angles. They must also lie parallel to a conductor's surface, otherwise this would produce a force that will move the charge carriers to even the potential of the surface. The electric field was formally defined as the force exerted per unit charge, but the concept of potential allows for a more useful and equivalent definition. The electric field is the local gradient of the electric potential. Usually expressed in volts per meter, the vector direction of the field is the line of greatest slope of potential, and where the equipotentials lie closest together. Electromagnets. Main article, electromagnets. A wire carries a current towards the reader. Concentric circles representing the magnetic field circle anti-clockwise around the wire, as viewed by the reader. Magnetic field circles around a current. Ørsted's discovery in 1821 that a magnetic field existed around all sides of a wire carrying an electric current indicated that there was a direct relationship between electricity and magnetism. Moreover, the interaction seemed different from gravitational and electrostatic forces, the two forces of nature then known. The force on the compass needle did not direct it to or away from the current-carrying wire, but acted at right angles to it. Ørsted's words were that the electric conflict acts in a revolving manner. The force also depended on the direction of the current, for if the flow was reversed, then the force did too. Ørsted did not fully understand his discovery, but he observed the effect was reciprocal. A current exerts a force on a magnet, and a magnetic field exerts a force on a current. The phenomenon was further investigated by Ampere, who discovered that two parallel current-carrying wires exerted a force upon each other. Two wires conducting currents in the same direction are attracted to each other, while wires containing currents in opposite directions are forced apart. The interaction is mediated by the magnetic field each current produces and forms the basis for the international definition of the ampere. A cutaway diagram of a small electric motor. The electric motor exploits an important effect of electromagnetism. A current through a magnetic field experiences a force at right angles to both the field and current. This relationship between magnetic fields and currents is extremely important, for it led to Michael Faraday's invention of the electric motor in 1821. Faraday's homopolar motor consisted of a permanent magnet sitting in a pool of mercury. A current was allowed through a wire suspended from a pivot above the magnet and dipped into the mercury. The magnet exerted a tangential force on the wire, making it circle around the magnet for as long as the current was maintained. Experimentation by Faraday in 1831 revealed that a wire moving perpendicular to a magnetic field developed a potential difference between its ends. Further analysis of this process, known as electromagnetic induction, enabled him to state the principle, now known as Faraday's law of induction, that the potential difference induced in a closed circuit is proportional to the rate of change of magnetic flux through the loop. Exploitation of this discovery enabled him to invent the first electrical generator in 1831, in which he converted the mechanical energy of a rotating copper disk to electrical energy. Faraday's disk was inefficient and of no use as a practical generator, but it showed the possibility of generating electric power using magnetism, a possibility that would be taken up by those that followed on from his work. Electric circuits. Main article, Electric circuit. A basic electric circuit. The voltage source V on the left drives a current I around the circuit, delivering electrical energy into the resistor R. From the resistor, the current returns to the source, completing the circuit. An electric circuit is an interconnection of electric components such that electric charge is made to flow along a closed path, a circuit, usually to perform some useful task. The components in an electric circuit can take many forms, which can include elements such as resistors, capacitors, switches, transformers and electronics. Electronic circuits contain active components, usually semiconductors, and typically exhibit nonlinear behavior, requiring complex analysis. The simplest electric components are those that are termed passive and linear. While they may temporarily store energy, they contain no sources of it, and exhibit linear responses to stimuli. The resistor is perhaps the simplest of passive circuit elements. As its name suggests, it resists the current through it, dissipating its energy as heat. The resistance is a consequence of the motion of charge through a conductor. In metals, for example, resistance is primarily due to collisions between electrons and ions. Ohm's law is a basic law of circuit theory, stating that the current passing through a resistance is directly proportional to the potential difference across it. The resistance of most materials is relatively constant over a range of temperatures and currents. Materials under those conditions are known as ohmic. The ohm, the unit of resistance, was named in honor of Georg Ohm, and is symbolized by the Greek letter 1. Is the resistance that will produce a potential difference of 1 volt in response to a current of 1 amp. The capacitor is a development of the Leyden jar and is a device that can store charge, and thereby storing electrical energy in the resulting field. It consists of 2 conducting plates separated by a thin insulating dielectric layer. In practice, thin metal foils are coiled together, increasing the surface area per unit volume and therefore the capacitance. The unit of capacitance is the farad, named after Michael Faraday, and given the symbol F. 1 farad is the capacitance that develops a potential difference of 1 volt when it stores a charge of 1 coulomb. A capacitor connected to a voltage supply initially causes a current as it accumulates charge. This current will however decay in time as the capacitor fills, eventually falling to zero. A capacitor will therefore not permit a steady-state current, but instead blocks it. The inductor is a conductor, usually a coil of wire, that stores energy in a magnetic field in response to the current through it. When the current changes, the magnetic field does too, inducing a voltage between the ends of the conductor. The induced voltage is proportional to the time rate of the change of the current. The constant of proportionality is termed the inductance. The unit of inductance is the Henry, named after Joseph Henry, a contemporary of Faraday. 1 Henry is the inductance that will induce a potential difference of 1 volt if the current through it changes at a rate of 1 ampere per second. The inductor's behavior is in some regards converse to that of the capacitor. It will freely allow an unchanging current, but opposes a rapidly changing one. Electronics. Main article, Electronics. Surface mount electronic components. Electronics deals with electrical circuits that involve active electrical components such as vacuum tubes, transistors, diodes, optoelectronics, sensors and integrated circuits, and associated passive interconnection technologies. The nonlinear behavior of active components and their ability to control electron flows makes amplification of weak signals possible, and electronics is widely used in information processing, telecommunications, and signal processing. The ability of electronic devices to act as switches makes digital information processing possible. Interconnection technologies such as circuit boards, electronics packaging technology, and other varied forms of communication infrastructure complete circuit functionality and transform the mixed components into a regular working system. Today, most electronic devices use semiconductor components to perform electron control. The study of semiconductor devices and related technology is considered a branch of solid-state physics, whereas the design and construction of electronic circuits to solve practical problems come under electronics engineering. Generation and transmission. Main article, Electricity generation. See also, Electric power transmission and mains electricity. Early 20th century alternator made in Budapest, Hungary, in the power generating hall of a hydroelectric station, photographed by Prokudin-Gorsky, 1905 to 1915. In the 6th century BC, the Greek philosopher Thales of Miletus experimented with amber rods, and these experiments were the first studies into the production of electrical energy. While this method, now known as the triboelectric effect, can lift light objects and generate sparks, it is extremely inefficient. It was not until the invention of the voltaic pile in the 18th century that a viable source of electricity became available. The voltaic pile, and its modern descendant, the electrical battery, store energy chemically and make it available on demand in the form of electrical energy. The battery is a versatile and very common power source which is ideally suited to many applications, but its energy storage is finite, and once discharged it must be disposed of or recharged. For large electrical demands, electrical energy must be generated and transmitted continuously over conductive transmission lines. Electrical power is usually generated by electromechanical generators driven by steam produced from fossil fuel combustion, or the heat released from nuclear reactions, or from other sources such as kinetic energy extracted from wind or flowing water. The modern steam turbine invented by Sir Charles Parsons in 1884 today generates about 80% of the electric power in the world using a variety of heat sources. Such generators bear no resemblance to Faraday's homopolar disk generator of 1831, but they still rely on his electromagnetic principle that a conductor linking a changing magnetic field induces a potential difference across its ends. The invention in the late 19th century of the transformer meant that electrical power could be transmitted more efficiently at a higher voltage but lower current. Efficient electrical transmission meant in turn that electricity could be generated at centralized power stations, where it benefited from economies of scale, and then be dispatched relatively long distances to where it was needed. A wind farm of about a dozen three-bladed white wind turbines. Wind power is of increasing importance in many countries. Since electrical energy cannot easily be stored in quantities large enough to meet demands on a national scale, at all times exactly as much must be produced as is required. This requires electricity utilities to make careful predictions of their electrical loads, and maintain constant coordination with their power stations. A certain amount of generation must always be held in reserve to cushion an electrical grid against inevitable disturbances and losses. Demand for electricity grows with great rapidity as a nation modernizes and its economy develops. The United States showed a 12% increase in demand during each year of the first 3 decades of the 20th century, a rate of growth that is now being experienced by emerging economies such as those of India or China. Historically, the growth rate for electricity demand has outstripped that for other forms of energy. Environmental concerns with electricity generation have led to an increased focus on generation from renewable sources, in particular from wind and solar. While debate can be expected to continue over the environmental impact of different means of electricity production, its final form is relatively clean. Fire. Fire is the rapid oxidation of a material, the fuel, in the exothermic chemical process of combustion, releasing heat, light, and various reaction products. Fire is hot because the conversion of the weak double bond in molecular oxygen, O2, to the stronger bonds in the combustion products carbon dioxide and water releases energy, 418 kilojoules per 32 grams of O2. The bond energies of the fuel play only a minor role here. At a certain point in the combustion reaction, called the ignition point, flames are produced. The flame is the visible portion of the fire. Flames consist primarily of carbon dioxide, water vapor, oxygen and nitrogen. If hot enough, the gases may become ionized to produce plasma. Depending on the substances alight, and any impurities outside, the color of the flame and the fire's intensity will be different. Fire in its most common form can result in conflagration, which has the potential to cause physical damage through burning. Fire is an important process that affects ecological systems around the globe. The positive effects of fire include stimulating growth and maintaining various ecological systems. Its negative effects include hazard to life and property, atmospheric pollution, and water contamination. If fire removes protective vegetation, heavy rainfall may lead to an increase in soil erosion by water. Also, when vegetation is burned, the nitrogen it contains is released into the atmosphere, unlike elements such as potassium and phosphorus which remain in the ash and are quickly recycled into the soil. This loss of nitrogen caused by a fire produces a long-term reduction in the fertility of the soil, but this fecundity can potentially be recovered as molecular nitrogen in the atmosphere is fixed and converted to ammonia by natural phenomena such as lightning and by leguminous plants that are nitrogen-fixing such as clover, peas, and green beans. Fire has been used by humans in rituals, in agriculture for clearing land, for cooking, generating heat and light, for signaling, propulsion purposes, smelting, forging, incineration of waste, cremation, and as a weapon or mode of destruction. Chemistry. Fires start when a flammable or combustible material, in combination with the sufficient quantity of an oxidizer such as oxygen gas or another oxygen-rich compound, though non-oxygen oxidizers exist, is exposed to a source of heat or ambient temperature above the flash point for the fuel oxidizer mix, and is able to sustain a rate of rapid oxidation that produces a chain reaction. This is commonly called the fire tetrahedron. Fire cannot exist without all of these elements in place and in the right proportions. For example, a flammable liquid will start burning only if the fuel and oxygen are in the right proportions. Some fuel-oxygen mixes may require catalyst, a substance that is not consumed, when added, in any chemical reaction during combustion, but which enables the reactants to combust more readily. Once ignited, a chain reaction must take place whereby fires can sustain their own heat by the further release of heat energy in the process of combustion and may propagate, provided there is a continuous supply of an oxidizer and fuel. If the oxidizer is oxygen from the surrounding air, the presence of a force of gravity, or of some similar force caused by acceleration, is necessary to produce convection, which removes combustion products and brings a supply of oxygen to the fire. Without gravity, a fire rapidly surrounds itself with its own combustion products and non-oxidizing gases from the air, which exclude oxygen and extinguish the fire. Because of this, the risk of fire in a spacecraft is small when it is coasting in inertial flight. This does not apply if oxygen is supplied to the fire by some process other than thermal convection. Fire can be extinguished by removing any one of the elements of the fire tetrahedron. Consider a natural gas flame, such as from a stovetop burner. The fire can be extinguished by any of the following. Turning off the gas supply, which removes the fuel source. Covering the flame completely, which smothers the flame as the combustion both uses the available oxidizer, the oxygen in the air, and displaces it from the area around the flame with CO2. Application of water, which removes heat from the fire faster than the fire can produce it. Similarly, blowing hard on a flame will displace the heat of the currently burning gas from its fuel source, to the same end, or application of a retardant chemical such as hail onto the flame, which retards the chemical reaction itself until the rate of combustion is too slow to maintain the chain reaction. In contrast, fire is intensified by increasing the overall rate of combustion. Methods to do this include balancing the input of fuel and oxidizer to stoichiometric proportions, increasing fuel and oxidizer input in this balanced mix, increasing the ambient temperature so the fire's own heat is better able to sustain combustion, or providing a catalyst, a non-reactant medium in which the fuel and oxidizer can more readily react. Flame. Main article, flame. See also, flame test. A candle's flame. Northwest Crown Fire Experiment, Canada. Photo of a fire taken with the 1/4000th of a second exposure. Fire is affected by gravity. Left, flame on Earth. Right, flame on the ISS. A flame is a mixture of reacting gases and solids emitting visible, infrared, and sometimes ultraviolet light, the frequency spectrum of which depends on the chemical composition of the burning material and intermediate reaction products. In many cases, such as the burning of organic matter, for example wood, or the incomplete combustion of gas, incandescent solid particles called soot produce the familiar red-orange glow of fire. This light has a continuous spectrum. Complete combustion of gas has a dim blue color due to the emission of single-wavelength radiation from various electron transitions in the excited molecules formed in the flame. Usually oxygen is involved, but hydrogen burning in chlorine also produces a flame, producing hydrogen chloride, HCl. Other possible combinations producing flames, amongst many, are fluorine and hydrogen, and hydrazine and nitrogen tetroxide. Hydrogen and hydrazine DMH flames are similarly pale blue, while burning boron and its compounds, evaluated in mid-20th century as a high-energy fuel for jet and rocket engines, emits intense green flame, leading to its informal nickname of Green Dragon. The glow of a flame is complex. Blackbody radiation is emitted from soot, gas, and fuel particles, though the soot particles are too small to behave like perfect blackbodies. There is also photon emission by the excited atoms and molecules in the gases. Much of the radiation is emitted in the visible and infrared bands. The color depends on temperature for the blackbody radiation, and on chemical makeup for the emission spectra. The dominant color in a flame changes with temperature. The photo of the forest fire in Canada is an excellent example of this variation. Near the ground, where most burning is occurring, the fire is white, the hottest color possible for organic material in general, or yellow. Above the yellow region, the color changes to orange, which is cooler, then red, which is cooler still. Above the red region, combustion no longer occurs, and the uncombusted carbon particles are visible as black smoke. The common distribution of a flame under normal gravity conditions depends on convection, as soot tends to rise to the top of a general flame, as in a candle in normal gravity conditions, making it yellow. In microgravity or zero gravity, such as an environment in outer space, convection no longer occurs, and the flame becomes spherical, with a tendency to become more blue and more efficient, although it may go out if not moved steadily, as the CO2 from combustion does not disperse as readily in microgravity, and tends to smother the flame. There are several possible explanations for this difference, of which the most likely is that the temperature is sufficiently evenly distributed that soot is not formed and complete combustion occurs. Experiments by NASA reveal that the fusion flames in microgravity allow more soot to be completely oxidized after they are produced in diffusion flames on Earth, because of a series of mechanisms that behave differently in microgravity when compared to normal gravity conditions. These discoveries have potential applications in applied science and industry, especially concerning fuel efficiency. In combustion engines, various steps are taken to eliminate a flame. The method depends mainly on whether the fuel is oil, wood, or a high-energy fuel such as jet fuel. Continents. North America. North America is a continent in the Northern Hemisphere and almost entirely within the Western Hemisphere. It can also be described as the northern subcontinent of a single continent, America. It is bordered to the north by the Arctic Ocean, to the east by the Atlantic Ocean, to the southeast by South America and the Caribbean Sea, and to the west and south by the Pacific Ocean. Because it is on the North American tectonic plate, Greenland is included as part of North America geographically. North America covers an area of about 24,709,000 square kilometers, 9,540,000 square miles, about 16.5% of the Earth's land area and about 4.8% of its total surface. North America is the third largest continent by area, following Asia and Africa, and the fourth by population after Asia, Africa, and Europe. In 2013, its population was estimated at nearly 579 million people in 23 independent states, or about 7.5% of the world's population. In human geography and in the English-speaking world outside the United States, particularly in Canada, North America and North American can refer to just Canada and the United States together. North America was reached by its first human populations during the last glacial period, via crossing the Bering Land Bridge approximately 40,000 to 17,000 years ago. The so-called Paleo-Indian period is taken to have lasted until about 10,000 years ago, the beginning of the Archaic or Meso-Indian period. The classic stage spans roughly the 6th to 13th centuries. The first recorded Europeans to visit North America, other than Greenland, were the Norse around 1000 AD. Christopher Columbus's arrival in 1492 sparked the transatlantic exchange, which included migrations of European settlers during the Age of Discovery and the early modern period. Present-day cultural and ethnic patterns reflect interactions between European colonists, indigenous peoples, African slaves, immigrants from Europe, Asia, and the descendants of these groups. Owing to Europe's colonization of the Americas, most North Americans speak European languages such as English, Spanish or French, and their cultures commonly reflect Western traditions. However, in parts of Canada, the United States, Mexico, and Central America, there are indigenous populations continuing their cultural traditions and speaking their own languages. Geography. Landforms and land cover of North America. Main article, Geography of North America. North America occupies the northern portion of the landmass generally referred to as the New World, the Western Hemisphere, the Americas, or simply America, which, in many countries is considered as a single continent with North America a subcontinent. North America is the third largest continent by area, following Asia and Africa. North America's only land connection to South America is at the Isthmus of Darien, Isthmus of Panama. The continent is delimited on the southeast by most geographers at the Darien watershed along the Colombia-Panama border, placing almost all of Panama within North America. Alternatively, some geologists physiographically locate its southern limit at the Isthmus of Tehuantepec, Mexico, with Central America extending southeastward to South America from this point. The Caribbean islands, or West Indies, are considered part of North America. The continental coastline is long and irregular. The Gulf of Mexico is the largest body of water indenting the continent, followed by Hudson Bay. Others include the Gulf of St. Lawrence and the Gulf of California. Before the Central American Isthmus formed, the region had been underwater. The islands of the West Indies delineate the submerged former land bridge, which had connected North and South America via what are now Florida and Venezuela. There are numerous islands off the continent's coasts, principally the Arctic archipelago, the Bahamas, Turks and Caicos, the Greater and Lesser Antilles, the Aleutian Islands, some of which are in the Eastern Hemisphere proper, the Alexander Archipelago, the many thousand islands of the British Columbia coast, and Newfoundland. Greenland, a self-governing Danish island, and the world's largest, is on the same tectonic plate, the North American plate, and is part of North America geographically. In a geologic sense, Bermuda is not part of the Americas, but an oceanic island that was formed on the fissure of the mid-Atlantic ridge over 100 million years ago. The nearest landmass to it is Cape Hatteras, North Carolina. However, Bermuda is often thought of as part of North America, especially given its historical, political and cultural ties to Virginia and other parts of the continent. The vast majority of North America is on the North American plate. Parts of western Mexico, including Baja California, and of California, including the cities of San Diego, Los Angeles, and Santa Cruz, lie on the eastern edge of the Pacific Plate, with the two plates meeting along the San Andreas Fault. The southernmost portion of the continent and much of the West Indies lie on the Caribbean Plate, whereas the Juan de Fuca and Cocos Plates border the North American Plate on its western frontier. The continent can be divided into four great regions, each of which contains many subregions: the Great Plains stretching from the Gulf of Mexico to the Canadian Arctic, the geologically young, mountainous West, including the Rocky Mountains, the Great Basin, California and Alaska, the raised but relatively flat plateau of the Canadian Shield in the northeast, and the varied eastern region, which includes the Appalachian Mountains, the coastal plain along the Atlantic seaboard, and the Florida Peninsula. Mexico, with its long plateaus and cordilleras, falls largely in the western region, although the eastern coastal plain does extend south along the Gulf. The western mountains are split in the middle into the main range of the Rockies and the Coast Ranges in California, Oregon, Washington, and British Columbia, with the Great Basin, a lower area containing smaller ranges and low-lying deserts, in between. The highest peak is Denali in Alaska. The United States Geographical Survey, USGS, states that the geographic center of North America is 6 miles, 10 kilometers, west of Balta, Pierce County, North Dakota, at about 48 degrees and 10 minutes north, 100 degrees and 10 minutes west, about 24 kilometers, 15 miles, from Rugby, North Dakota. The USGS further states that no marked or monumented point has been established by any government agency as the geographic center of either the 50 states, the conterminous United States, or the North American continent. Nonetheless, there is a 4.6-meter (15 feet) fieldstone obelisk in Rugby claiming to mark the center. The North American continental pole of inaccessibility is located 1,650 kilometers, 1,030 miles, from the nearest coastline, between Allen and Kyle, South Dakota, at 43.36 degrees north, 101.97 degrees west. Languages. Main article, Languages of North America. Native languages of the U.S., Canada, Greenland, and northern Mexico. The dominant languages in North America are English, Spanish, and French. Danish is prevalent in Greenland alongside Greenlandic, and Dutch is spoken side by side local languages in the Dutch Caribbean. The term Anglo-America is used to refer to the Anglophone countries of the Americas, namely Canada, where English and French are co-official, and the United States, but also sometimes Belize and parts of the tropics, especially the Commonwealth Caribbean. Latin America refers to the other areas of the Americas, generally south of the United States, where the Romance languages, derived from Latin, of Spanish and Portuguese, but French-speaking countries are not usually included, predominate. The other republics of Central America, but not always Belize, part of the Caribbean, not the Dutch, English, or French-speaking areas, Mexico, and most of South America, except Guyana, Suriname, French Guiana, France, and the Falkland Islands, UK. The French language has historically played a significant role in North America and now retains a distinctive presence in some regions. Canada is officially bilingual. French is the official language of the province of Quebec, where 95% of the people speak it as either their first or second language, and it is co-official with English in the province of New Brunswick. Other French-speaking locales include the province of Ontario. The official language is English, but there are an estimated 600,000 Franco-Ontarians. The province of Manitoba, co-official as de jure with English, the French West Indies and Saint Pierre et Miquelon, as well as the U.S. state of Louisiana, where French is also an official language. Haiti is included with this group based on historical association, but Haitians speak both Creole and French. Similarly, French and French Antillean Creole is spoken in St. Lucia and the Commonwealth of Dominique alongside English. A significant number of indigenous languages are spoken in North America, with 372,000 people in the United States speaking an indigenous language at home, about 225,000 in Canada and roughly 6 million in Mexico. In the United States and Canada, there are approximately 150 surviving indigenous languages of the 300 spoken prior to European contact. South America is a continent entirely in the Western Hemisphere and mostly in the Southern Hemisphere, with a relatively small portion in the Northern Hemisphere. It can also be described as the southern subregion of a single continent called America. South America is bordered on the west by the Pacific Ocean and on the north and east by the Atlantic Ocean. North America and the Caribbean Sea lie to the northwest. The continent generally includes 12 sovereign states: Argentina, Bolivia, Brazil, Chile, Colombia, Ecuador, Guyana, Paraguay, Peru, Suriname, Uruguay, and Venezuela, 2 dependent territories, the Falkland Islands in South Georgia and the South Sandwich Islands, and 1 internal territory, French Guiana. In addition, the ABC Islands of the Kingdom of the Netherlands, Ascension Island, dependency of St. Helena, Ascension and Tristan da Cunha, a British overseas territory, Bouvet Island, dependency of Norway, Panama, and Trinidad and Tobago may also be considered parts of South America. South America has an area of 17,840,000 square kilometers, 6,890,000 square miles. Its population as of 2018 has been estimated at more than 423 million. South America ranks 4th in area, after Asia, Africa, and North America, and 5th in population, after Asia, Africa, Europe, and North America. Brazil is by far the most populous South American country, with more than half of the continent's population, followed by Colombia, Argentina, Venezuela, and Peru. In recent decades, Brazil has also generated half of the continent's GDP and has become the continent's first regional power. Most of the population lives near the continent's western or eastern coasts, while the interior and the far south are sparsely populated. The geography of western South America is dominated by the Andes Mountains. In contrast, the eastern part contains both highland regions and vast lowlands where rivers such as the Amazon, Orinoco and Parana flow. Most of the continent lies in the tropics, except for a large part of the southern cone located in the middle latitudes. The continent's cultural and ethnic outlook has its origin with the interaction of indigenous peoples with European conquerors and immigrants and, more locally, with African slaves. Given a long history of colonialism, the overwhelming majority of South Americans speak Spanish or Portuguese, and societies and states are rich in Western traditions. Relative to Europe, Asia, and Africa, 20th century South America has been a peaceful continent with few wars. South America occupies the southern portion of the Americas. The continent is generally delimited on the northwest by the Darien watershed along the Colombia-Panama border, although some may consider the border instead to be the Panama Canal. Geopolitically and geographically, all of Panama, including the segment east of the Panama Canal in the Isthmus, is typically included in North America alone and among the countries of Central America. Almost all of mainland South America sits on the South American plate. South America is home to the world's highest uninterrupted waterfall, Angel Falls in Venezuela, the highest single-drop waterfall Catur Falls in Guyana, the largest river by volume, the Amazon River, the longest mountain range, the Andes, whose highest mountain is Aconcagua at 6,962 meters or 22,841 feet, the driest non-polar place on Earth, the Atacama Desert, the wettest place on Earth, Lopez de Maquis in Colombia, the largest rainforest, the Amazon rainforest, the highest capital city, La Paz, Bolivia, the highest commercially navigable lake in the world, Lake Titicaca, and, excluding research stations in Antarctica, the world's southernmost permanently inhabited community, Puerto Toro, Chile. South America's major mineral resources are gold, silver, copper, iron ore, tin, and petroleum. These resources found in South America have brought high income to its countries, especially in times of war or of rapid economic growth by industrialized countries elsewhere. However, the concentration in producing one major export commodity often has hindered the development of diversified economies. The fluctuation in the price of commodities in the international markets has led historically to major highs and lows in the economies of South American states, often causing extreme political instability. This is leading to efforts to diversify production to drive away from staying as economies dedicated to one major export. Brazil is the largest country in South America, covering a little less than half of the continent's land area and encompassing around half of the continent's population. The remaining countries and territories are divided among four subregions: the Andean states, Caribbean South America, the Guianas, and the Southern Cone. Language. Official languages in South America. Spanish and Portuguese are the most spoken languages in South America, with approximately 200 million speakers each. Spanish is the official language of most countries, along with other native languages in some countries. Portuguese is the official language of Brazil. Dutch is the official language of Suriname. English is the official language of Guyana, although there are at least 12 other languages spoken in the country, including Portuguese, Chinese, Hindustani, and several native languages. English is also spoken in the Falkland Islands. French is the official language of French Guiana and the second language in Amapa, Brazil. Indigenous languages of South America include Quechua in Peru, Bolivia, Ecuador, Chile and Colombia, Huayhenque in northern Colombia, La Guajira, and northwestern Venezuela, Zulia, Guarani in Paraguay and, to a much lesser extent, in Bolivia, Aymara in Bolivia, Peru, and less often in Chile, and Mapudangan is spoken in certain pockets of southern Chile. At least 3 South American indigenous languages, Quechua, Aymara, and Guarani, are recognized along with Spanish as national languages. Other languages found in South America include Hindustani and Javanese in Suriname, Italian in Argentina, Brazil, Uruguay and Venezuela, and German in certain pockets of Argentina and Brazil. German is also spoken in many regions of the southern states of Brazil, Rio Grande and Sergipe being the most widely spoken German dialect in the country. Among other Germanic dialects, a Brazilian form of East Pomeranian is also well represented and is experiencing a revival. Welsh remains spoken and written in the historic towns of Trelew and Rawson in the Argentine Patagonia. There are also small clusters of Japanese speakers in Brazil, Colombia, and Peru. Arabic speakers, often of Lebanese, Syrian, or Palestinian descent, can be found in Arab communities in Argentina, Colombia, Brazil, Venezuela and in Paraguay. Australia. The continent of Australia is located in the southern hemisphere. The continent is sometimes defined as mainland Australia and Tasmania along with smaller surrounding islands. At other times the continent is defined as including the island of New Guinea, which lies on the same continental shelf, and its surrounding smaller islands along with Australia. Australia only. The continent of Australia is sometimes defined as including mainland Australia and its surrounding islands including Tasmania, making it the world's smallest continent. When this definition is used, Australia is the world's only continent that is governed by a single nation-state, Australia. When defined as only Australia, the continent is approximately 7,690,000 square kilometers, 2,970,000 square miles, in size. It is the world's lowest-lying continent. Its highest point is Mount Kosciuszko with an elevation of 2,228 meters, 7,310 feet. The lowest point is Lake Eyre, which is 15 meters, 49 feet, below sea level, and the continent's average elevation is 330 meters, 1,080 feet. Australia and New Guinea. The continent of Australia is also sometimes defined as encompassing a larger area, being the Australian mainland, Tasmania and the island of New Guinea, all of which share a shallow continental shelf. 5. This definition encompasses all of the modern land masses that at times of lower sea levels were encompassed in the prehistoric continent referred to as Sol. With the inclusion of New Guinea, the continent is governed by 3 nation-states, Australia, Papua New Guinea, and Indonesia, which governs Western New Guinea. Under this definition, New Guinea represents a mountainous northern margin of the Australian continent, as New Guinea is one of the most mountainous islands in the world. The highest point in New Guinea is Puncak Jaya with an elevation of 4,884 meters, 16,024 feet. The combined area of Australia, New Guinea and Tasmania is approximately 8,500,000 square kilometers, 3,300,000 square miles. Oceania. Oceania is a geographic region that includes Australasia, Melanesia, Micronesia, and Polynesia. Spanning the eastern and western hemispheres, Oceania is estimated to have a land area of 8,525,989 square kilometers, 3,291,903 square miles, and a population of over 41 million. When compared with the continents, the region of Oceania is the smallest in land area and the second smallest in population after Antarctica. Oceania has a diverse mix of economies from the highly developed and globally competitive financial markets of Australia, New Caledonia, New Zealand, French Polynesia, and Hawaii, which rank high in quality of life and Human Development Index 7-8, to the much less developed economies such as Papua New Guinea, Indonesian New Guinea, Kiribati, Vanuatu, and Tuvalu, while also including medium-sized economies of Pacific islands such as Palau, Fiji, and Tonga. The largest and most populous country in Oceania is Australia, and the largest city is Sydney. The first settlers of Australia, New Guinea, and the large islands just to the east arrived more than 60,000 years ago. Oceania was first explored by Europeans from the 16th century onward. Portuguese explorers between 1512 and 1526 reached the Tanimbar Islands, some of the Caroline Islands and West Papua New Guinea. On his first voyage in the 18th century, James Cook, who later arrived at the highly developed Hawaiian Islands, went to Tahiti and followed the east coast of Australia for the first time. The Pacific Front saw major action during the Second World War, mainly between Allied powers the United States, Philippines, a U.S. Commonwealth at the time, and Australia, and Axis power Japan. The arrival of European settlers in subsequent centuries resulted in a significant alteration in the social and political landscape of Oceania. In more contemporary times there has been increasing discussion on national flags and a desire by some Oceanians to display their distinguishable and individualistic identity. The rock art of Aboriginal Australia